What if everything you thought you knew about reality was only a fraction of the story? Picture this: a universe not as a fixed, external stage, but as something deeply interactive, almost responsive, shaped in ways we are only beginning to understand. The great physicist John Wheeler once captured this mystery perfectly when he said, "The universe does not exist out there, independent of us. We are inescapably involved in bringing about that which appears to be happening." That single idea invites us into one of the most thrilling and humbling questions science has ever asked. What is the true nature of reality, and how much of it remains hidden just beyond the edges of our current understanding? Throughout history, brilliant minds have dared to look closer, and in doing so, they've uncovered breathtaking truths that challenge our most basic assumptions. Yet not every groundbreaking idea makes it into the textbooks. Some fade into the background, overshadowed by more popular theories, technological limitations, or simply because they were too far ahead of their time. This video is about those forgotten breakthroughs, 30 of them, each a missing piece in the grand puzzle of existence. From the spooky connections of quantum entanglement to the mind-bending possibilities of the multiverse, these are the concepts that traditional science sometimes overlooked, dismissed, or set aside. But what if revisiting them now could change everything we believe about space, time, and our place in the cosmos? You're about to embark on a journey through the hidden corridors of scientific history, where we'll dust off theories that languished in obscurity and explore why they matter now more than ever. We'll meet the visionaries who saw further than their peers and ask why their ideas were sidelined only to resurface with revolutionary implications decades later. This isn't just a list of obscure facts, it's an investigation into the shape of reality itself. So get ready to question what you think you know, to wonder, and to see the universe in a whole new light. Because sometimes the most extraordinary truths are waiting right where we least expect them. Long before laboratories and particle accelerators, the human quest to understand reality began under the open skies of ancient Greece. Philosophers like Democritus gazed at the heavens and proposed a stunning idea that everything we see might be composed of tiny, indivisible particles he called atoms, moving through a void. This early form of atomism was a radical departure from mythological explanations, suggesting the cosmos operated on underlying physical principles. Around the same time, Plato offered a different but equally profound metaphor with his allegory of the cave. He asked us to imagine people chained since birth, seeing only shadows cast on a wall by a fire behind them. For these prisoners, the shadows are the entirety of their reality. Plato's point was that our own perceptions might be just as limited, mere flickering shadows of a deeper, truer reality that exists beyond our immediate senses. These two ancient thought experiments set the stage for a tension that would define science for millennia. Is reality fundamentally made of discrete, physical stuff, or is our experience of it a kind of illusion? This philosophical groundwork waited centuries for the tools to test its ideas. The scientific revolution, ignited by figures like Galileo and Newton, delivered those tools and seemed to settle the debate firmly in favor of a physical, mechanical universe. Isaac Newton's laws of motion and universal gravitation painted a picture of a cosmos that was vast, predictable, and elegant, a grand clockwork machine where every tick of the clock and every orbit of a planet could, in principle, be calculated if you knew the initial conditions. This deterministic view was incredibly powerful. It suggested that the future was already written into the present, a cosmic billiards game where the paths of all particles were predetermined from the moment of creation. For over 200 years, this clockwork universe was the prevailing paradigm, giving humanity immense predictive power and a sense that reality was, at its heart, knowable and objective. Yet, by the dawn of the 20th century, cracks began to appear in this magnificent clockwork edifice. The discovery of phenomena that Newtonian mechanics couldn't explain, like the precise nature of light or the behavior of atoms, ushered in a period of tremendous upheaval. This was the birth of quantum theory, and it forced the greatest minds of a generation to confront questions that sounded more like philosophy than physics. The calm certainty of a deterministic universe was shattered, replaced by a bizarre realm of probability and paradox. At the forefront of this revolution were figures like Albert Einstein, Niels Bohr, and Erwin Schrödinger, who engaged in fierce, passionate debates that were as much about the nature of reality itself as they were about equations. Einstein, deeply uncomfortable with the inherent randomness, insisted that God does not play dice with the universe. He clung to the belief that an objective reality existed independent of any observer. Bohr, on the other hand, argued that we cannot separate the phenomenon from the measurement, that the act of observation itself shapes the outcome, making reality, in some fundamental way, participant-dependent. It was within this cauldron of intellectual ferment that many of the breakthroughs we'll explore first emerged. They were products of their time, born from the struggle to reconcile the classical world of certainty with the quantum world of ambiguity. However, the very reasons they were so revolutionary are also why so many were sidelined or forgotten. Some ideas, like quantum entanglement, were dismissed as philosophical quirks because the technology to test them didn't yet exist. Others, like proposals involving multiple universes or a holographic cosmos, were too radical, too threatening to the established scientific worldview, or too entangled with metaphysical implications that made the mainstream scientific community uncomfortable. They were often pushed to the fringes, seen as interesting but untestable speculations. Understanding this historical context is crucial. It reminds us that the path of science is not a straight, clean line toward truth, but a messy, human endeavor filled with dead ends, overlooked gems, and ideas that were simply ahead of their time. Revisiting them today with new technology and fresh perspectives allows us to see these forgotten breakthroughs not as failures, but as premature revelations, keys to unlocking a deeper understanding of the shape of reality. It was into this heated debate over the fundamental nature of reality that Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, launched a direct and brilliant assault. In 1935, they published a paper that was intended not to explore a new idea, but to expose what they saw as a fatal flaw in the now dominant Copenhagen interpretation of quantum mechanics. Their goal was to prove that quantum theory, with its probabilistic and observer-dependent claims, was an incomplete description of the universe. They constructed an elegant thought experiment, now famously known as the EPR Paradox, designed to show that the theory necessarily led to a conclusion so absurd that it had to be wrong. The crux of their argument hinged on a concept they called entanglement. Imagine a single particle that decays into two new particles, which then fly off in opposite directions across the universe. According to the quantum rules that govern their creation, certain properties of these two particles, like their spin or polarization, would be intrinsically linked or entangled. The Copenhagen interpretation said that these properties don't have a definite value until they are measured. So, if a physicist on one side of the galaxy measures the spin of her particle and finds it is up, the spin of the other particle, instantly and regardless of the immense distance separating them, must become down. This implied a connection that communicated faster than the speed of light, a notion that violated Einstein's own theory of relativity, which held that nothing could exceed that cosmic speed limit. He famously derided this bizarre consequence as spooky action at a distance, insisting that no sane description of reality could allow for such a thing. For Einstein, Podolsky, and Rosen, this spookiness was proof that quantum mechanics was not the final word. They argued that there must be some deeper, hidden reality, what they called hidden variables, that predetermined the properties of the particles all along. The particles weren't communicating, they were simply following a script written at the moment of their creation, a script that quantum theory was simply too crude to read. The EPR paper was a powerful challenge, a gauntlet thrown down at the feet of Niels Bohr and his supporters. In many ways, it was a battle for the soul of physics, pitting Einstein's belief in a rational, objective, and local reality against Bohr's acceptance of a fuzzy, probabilistic, and interconnected one. And yet, despite the towering reputation of its authors, the EPR paradox was largely sidelined for decades. It was treated as a fascinating philosophical puzzle, a curious thought experiment for graduate students to debate, but not a pressing line of experimental inquiry. The physics community, eager to use the stunningly accurate predictive power of quantum mechanics to build lasers and transistors, largely moved on. The paradox was forgotten not because it was solved, but because it was considered unsolvable, a metaphysical debate with no way to test who was right in the real world. It seemed the universe would keep this secret forever. That is, until a soft-spoken Irish physicist named John Bell entered the scene almost 30 years later. In 1964, Bell devised a way to translate the philosophical EPR argument into a real, testable mathematical prediction. His work, now known as Bell's theorem, provided a clear experimental path to distinguish between Einstein's hidden variables and Bohr's spooky action. If Einstein was right, the results of certain particle measurements would stay within a specific statistical limit. But if quantum mechanics was correct, and particles could indeed influence each other across vast distances, those limits would be violated. The stage was set for a showdown. Throughout the 1970s and into the 80s, a series of pioneering experiments, most notably by French physicist Alain Aspect, meticulously put Bell's theorem to the test. The results were unequivocal and earth-shattering. The quantum predictions were confirmed again and again. Particles did indeed influence each other instantaneously, their fates intertwined in a way that defied classical intuition and any notion of local reality. Einstein was wrong, Bohr was right, the spooky action was real. This validation of the EPR paradox's central claim, though not its intended conclusion, utterly revolutionized our understanding of the universe. The forgotten thought experiment was suddenly the foundation for the new field of quantum information science. What Einstein had proposed as a reductio ad absurdum, a logical argument meant to destroy a theory, turned out to be one of the most profound features of nature. Entanglement is not a bug in reality, it is a fundamental feature. It is the engine behind the emerging technologies of quantum computing and quantum cryptography, which promise to reshape our world. The EPR paradox teaches us a humbling lesson about scientific progress. It shows that even our greatest geniuses can be limited by their own philosophical biases, and that ideas dismissed as too strange or counterintuitive may later be revealed as foundational truth. This forgotten breakthrough forces us to accept that the universe is deeply, mysteriously, and beautifully interconnected in ways we are only just beginning to grasp. If the implications of entanglement left us questioning the fundamental interconnectedness of our universe, the next forgotten breakthrough would challenge the very idea that there is only one universe to begin with. In the mid-1950s, a brilliant and unassuming PhD student named Hugh Everett Roman III was grappling with the same quantum measurement problem that had troubled Einstein. But where others saw a paradox to be solved, Everett saw an opportunity for a radical, breathtaking simplification. He asked a deceptively simple question: what if the wave function never actually collapses? What if, instead of one outcome being mysteriously selected at the moment of observation, every single possible outcome simply happens? His answer, laid out in his 1957 dissertation, was the many worlds interpretation of quantum mechanics. Everett proposed that the universe is described by a single, never-collapsing wave function that relentlessly and continuously splits or branches at every quantum event. In this view, there is no single, definitive reality. Instead, there is a vast, ever-expanding multiverse of parallel universes. In one branch of reality, a radioactive atom decays; in another, it does not. In one world, a photon goes through the left slit in the classic double-slit experiment. In another, it goes through the right. Every possible outcome that quantum mechanics allows is realized in its own separate, non-communicating universe. This wasn't just about particles, it was about everything. Every choice you've ever made, from what you had for breakfast to the career you pursued, has a counterpart in another world where you made a different decision. The version of you reading this script is just one thread in an infinite tapestry of existence. The reaction from the physics establishment, particularly from the towering figure of Niels Bohr, whose Copenhagen interpretation was dominant, was not merely skeptical, it was dismissive to the point of hostility. Everett's idea was labeled as philosophically extravagant, scientifically untestable, and perhaps worst of all, comically science-fictional. The notion of an infinite proliferation of universes seemed like an absurd waste of ontological resources, a violation of Occam's razor that multiplied entities beyond necessity. At a key meeting in Copenhagen, Bohr and his colleagues essentially brushed the young graduate student aside, offering little engagement with his mathematics and focusing only on what they saw as its fantastical conclusions. Deeply disillusioned by the cold reception and seeing no future for himself in academic physics, a disheartened Everett left the field entirely. He turned his formidable intellect to military operations research and computer modeling, and his revolutionary thesis gathered dust, a forgotten curiosity relegated to the fringes of quantum foundations. For decades, that's where it remained, but a fascinating thing began to happen as physics advanced. The problems that the Copenhagen interpretation swept under the rug with its vague notion of wave function collapse became harder to ignore, especially for cosmologists trying to apply quantum rules to the universe as a whole. If the universe is all there is, then who is the external observer that can collapse its wave function? The many worlds interpretation provided an elegant and paradox-free answer. There is no collapse and no need for an external observer. The entire universe just keeps on branching. This elegant solution to the measurement problem, along with the rise of quantum computing where superposition is a practical tool, led to a dramatic revival of interest in Everett's work from the 1980s onward. Physicists like David Deutsch became powerful advocates, arguing that far from being unscientific, the theory's predictions were the same as standard quantum mechanics. It just offered a far simpler and more coherent explanation for why those predictions hold true. The profound implication of Everett's forgotten breakthrough is that reality is not a single, linear timeline but a boundless multiverse of possibilities. The conscious experience you have right now is just one path being traced through this unimaginably vast tree of branching events. Somewhere out there in the multiverse, every potentiality is actualized. This isn't just a theory about physics, it's a theory about existence itself, forcing us to reconsider concepts of identity, choice, and chance. It suggests that the universe is not just stranger than we imagine, but stranger than we can imagine, with every quantum decision spawning new worlds in a cosmic process of endless becoming. Hugh Everett's legacy is a humbling and awe-inspiring reminder that a single idea, no matter how initially rejected, can eventually force us to expand our conception of reality to its absolute limits. While the many worlds interpretation asked us to expand our view of reality outward into infinite parallel universes, another brilliant and deeply unconventional physicist was inviting us to look inward to a hidden depth within the universe itself. David Bohm was not just a theorist, he was a protege of Einstein's and a respected quantum physicist in his own right. But he grew increasingly dissatisfied with what he saw as the fragmented and incomplete story told by the standard Copenhagen interpretation. He couldn't accept that reality was ultimately random, or that the role of the observer was a mysterious, unexplainable full stop in the equations. He believed there had to be a deeper, more coherent level of reality beneath the quantum weirdness, a hidden harmony where the paradoxes of the quantum world would make perfect sense. In the 1980s, after decades of contemplation, Bohm introduced his revolutionary concept of the implicate order. He proposed that what we perceive as reality is just the surface level, which he called the explicate order. This is the world of separate objects, definite locations, and clear cause and effect that we navigate every day. But beneath this surface, he argued, lies a far more fundamental and profound reality, the implicate order. The word implicate means enfolded, and that's precisely how Bohm saw this deeper layer. In the implicate order, everything in the universe is seamlessly interconnected and enfolded into a unified whole. Separation is an illusion. Every point in space and moment in time contains, in some sense, the entire cosmos. To make this astonishing idea tangible, Bohm offered a simple yet powerful analogy, the hologram. If you take a photographic hologram and cut it in half, you don't get half of the image. Instead, each half contains the entire image, just from a slightly different perspective. The whole is literally encoded in every single part. Bohm suggested that our universe might operate on a similar principle, that every electron, every star, and every human being is not an isolated thing but a unique projection of an underlying holographic totality. In this view, the apparent separateness of objects in our explicate world is like the distinct ripples on the surface of a stream. If we look deeper, we see that all the ripples are just temporary expressions of the same inseparable body of water, constantly flowing and changing form. Unsurprisingly, the mainstream physics community of the time largely marginalized Bohm's ideas. His theory was criticized for being more philosophy than physics, a metaphysical speculation that was beautiful but ultimately untestable. It ventured too far into the realm of the qualitative and the holistic for a discipline that was, and still is, firmly rooted in quantitative prediction and empirical verification. Without a clear mathematical framework to make testable predictions, Bohm's implicate order was gently set aside as a fascinating but ultimately unproductive line of inquiry, a poignant dream from a physicist who dared to think too far outside the box. Yet, as is so often the case with these forgotten breakthroughs, time has a way of vindicating visionaries. Decades after Bohm first proposed his ideas, they have experienced a remarkable renaissance, not directly through his own work, but through independent lines of inquiry in theoretical physics. The development of the holographic principle in the 1990s, particularly through the work of Gerard T. Hooft and Leonard Susskind, echoed Bohm's core insight in a startlingly precise way. This principle, which suggests that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, is a direct mathematical realization of the holographic metaphor. Furthermore, research into quantum gravity and the nature of spacetime increasingly points to the idea that space and time themselves are not fundamental. They may be emergent properties that arise from a more basic, non-local network of relationships, a concept that sounds remarkably similar to Bohm's vision of an enfolded, implicate reality, giving rise to our unfolded, explicate world. David Bohm's profound contribution is a powerful reminder that progress in science doesn't always move in a straight line. Sometimes the most transformative ideas are born from a willingness to ask bigger questions, to look beyond the prevailing paradigm, and to embrace a vision of reality that is more interconnected, more mysterious, and more beautiful than we had previously allowed ourselves to imagine. He taught us that sometimes, to truly understand the universe, we must be willing to see the whole in every part. If the nature of reality seems strange at the quantum scale, what about the nature of our own minds? For centuries, the phenomenon of consciousness has been the ultimate ghost in the machine, a deeply personal experience that remains one of science's greatest unsolved mysteries. How do the trillions of neurons firing in our brains give rise to the rich, unified, and subjective experience of being you, right here, right now? Most conventional neuroscience treats the brain as a sophisticated classical computer, a network of on-off switches processing information. But this view struggles to explain the holistic, integrated quality of awareness. It was into this conceptual gap that one of the most brilliant and controversial minds in modern physics dared to venture. Sir Roger Penrose, a Nobel laureate renowned for his groundbreaking work on black holes and general relativity, was deeply troubled by the standard interpretation of quantum mechanics. He was particularly unsatisfied with the idea of the wave function collapse, the moment a quantum probability resolves into a single, definite outcome. In the traditional Copenhagen view, this collapse is triggered by a conscious observer, a notion Penrose found circular and unscientific. If consciousness causes collapse, he argued, then what causes consciousness? It was an explanatory dead end. Penrose proposed a radical alternative. What if the collapse isn't triggered by observation, but is instead an objective, physical process? His theory, called objective reduction or OR, suggests that quantum superpositions are inherently unstable. They can't hold their fuzzy, multiple-state existence forever. The sheer mass of an object in superposition creates a tiny but fundamental tension in the fabric of spacetime itself. According to Penrose, it is this gravitational stress that ultimately forces the superposition to collapse into a single, classical state. This isn't a random event, but a precise, calculable process occurring at the unimaginably small Planck scale. In one breathtaking move, Penrose had removed the conscious observer from the center of the quantum mystery and replaced it with gravity, offering a bridge between the world of the very small and the very large. But Penrose didn't stop there. He then asked a question so audacious it would define his legacy. If objective reduction is a real physical process, could it be happening not just in the void of space, but right inside our heads? To explore this, he joined forces with Dr. Stuart Hameroff, an anesthesiologist whose work focused on the intricate structures within brain cells called microtubules. These tiny, cylindrical proteins form the skeleton of neurons, and Hameroff had long suspected they played a key role in organizing neural activity. Together, Penrose and Hameroff built a stunning hypothesis. Perhaps microtubules are small and isolated enough to support quantum vibrations, protected from the warm, wet, and disruptive environment of the brain. In their theory, these quantum vibrations persist in superposition until they reach a threshold of mass-time energy, at which point they undergo objective reduction, collapsing in accordance with Penrose's gravitational rules. And here is the most extraordinary part. they propose that each individual collapse event is a moment of proto-consciousness. A single one is nothing, a fleeting flicker. But billions of them, orchestrated across the brain's vast network, could together give rise to the full, flowing stream of our conscious experience. In this view, the brain isn't a classical computer, it's a quantum orchestra, and consciousness is the music it plays. The scientific reaction to what became known as the Penrose-Hameroff theory was, to put it mildly, fiercely critical. The established fields of neuroscience and physics have historically preferred to stay in their own lanes, and this theory bulldozed right through the median. Critics pounced on what they called the warm, wet, and noisy problem, the firm belief that quantum states are far too delicate to survive for any meaningful length of time in the chaotic environment of a living brain. Decoherence, the process by which quantum magic is destroyed by interaction with the environment, would smash any such delicate states almost instantly. To many, the idea seemed not just wrong but fanciful, a piece of scientific poetry that ignored the harsh realities of biophysics. The theory was largely dismissed and for a time forgotten by the mainstream, relegated to the fringes of both physics and biology. Yet, as with so many of these forgotten breakthroughs, new evidence is forcing a reluctant reevaluation. The emerging field of quantum biology is revealing that nature may have indeed found clever ways to harness quantum mechanics. We now know that photosynthesis in plants uses quantum coherence to achieve near-perfect energy transfer. Birds may use quantum entanglement in their eyes to navigate using the Earth's magnetic field. If quantum effects can play a functional role in green leaves and bird brains, is it really so impossible that they could be at work in our own? Recent experiments have even reported tentative evidence of quantum vibrations in microtubules, and new research is exploring how certain anesthetics, which selectively turn off consciousness, might work by interrupting these precise quantum processes. While far from conclusive, these findings suggest that Penrose and Hameroff's radical idea may not be as outlandish as once thought. Roger Penrose's objective reduction theory ultimately challenges us to confront the most profound possibility of all, that consciousness is not some emergent illusion or a simple byproduct of computation. It proposes that our inner experience is woven directly into the fundamental fabric of reality, a manifestation of the universe's quantum gravitational structure at the very smallest scale. It dares to suggest that the music of the mind and the laws of the cosmos are not separate symphonies, but different movements of the same grand composition. This forgotten breakthrough asks us to consider that to understand ourselves, we might first need to understand the very quantum geometry of spacetime. While we often marvel at the grand structures of the cosmos, the swirling galaxies, the burning stars, some of the most profound revelations about reality come from studying what appears to be absolutely nothing. The vacuum of space has long been imagined as a perfect, silent void, an empty stage upon which the drama of the universe plays out. But what if that stage itself is not empty at all? What if the void is, in fact, a seething, vibrant sea of energy? This is the incredible truth revealed by a deceptively simple prediction made in 1948 by a Dutch physicist named Hendrik Casimir. Casimir, working at the prestigious Phillips Research Laboratory, was exploring the forces that might act between closely spaced objects. He and his colleague Dirk Polder were initially studying the behavior of colloids, tiny particles suspended in a fluid. But Casimir's genius was to apply the strange new rules of quantum electrodynamics to this problem. He asked a fascinating question. If you take two perfectly smooth, uncharged metallic plates and place them incredibly close together in a perfect vacuum, what happens? Our classical intuition, shaped by Newton and Maxwell, would say nothing. With no electric charge and no gravity to speak of at that scale, the plates should just sit there, ignoring each other. But Casimir's calculations told a very different and utterly bizarre story. He predicted that the plates would be gently pulled together by an invisible, irresistible force. The explanation for this strange attraction lies in one of the most mind-bending concepts in all of physics, quantum fluctuations. According to quantum field theory, what we call a vacuum is not a true nothingness. Instead, it is a roiling foam of temporary activity. At every single point in space, pairs of virtual particles, a particle and its antiparticle, are constantly flickering into and out of existence, borrowing energy from the vacuum for an unimaginably brief moment before annihilating each other and paying the energy back. This ceaseless, frantic activity is known as the quantum foam, and it contributes to a background energy permeating all of space, called the zero-point energy because it exists even at absolute zero temperature. Now, here's where Casimir's plates come in. These virtual particles manifest as waves of different wavelengths. Think of the vacuum between the plates as being filled with a chaotic orchestra of every possible note. When the plates are brought extremely close together, closer than the width of a human hair, they act like a tiny, confining room. Only those virtual particles with wavelengths that can exactly fit between the plates, like sound waves resonating in a small chamber, are allowed to exist in that narrow gap. Outside the plates, however, virtual particles of all wavelengths can flourish. This creates a pressure imbalance. The riot of activity on the outside of the plates pushes them together with more force than the limited set of waves pushing from the inside. The result is a net, measurable force, the Casimir force. For decades, this was a beautiful but untested theoretical prediction, a curious footnote in quantum textbooks. The effect is incredibly subtle, requiring exquisitely smooth surfaces and precise control at the nanoscale. It wasn't until 1997, nearly 50 years after Casimir's paper, that technology finally caught up. Steve Lamoureux at Los Alamos National Laboratory, and later Yuma Mohideen and Anushree Roy at the University of California, Riverside, performed landmark experiments that confirmed the Casimir effect with stunning accuracy. They saw the plates snap together just as predicted, providing direct, tangible proof that empty space is alive with quantum energy. This validation moved the Casimir effect from a quantum quirk to a cornerstone of modern physics. Its implications are staggering, reaching from the infinitesimally small to the cosmologically vast. For nanotechnology, it's a very practical problem. This force can cause tiny machine parts to stick together, a phenomenon known as stiction that engineers must now account for. But its true profundity lies in cosmology. The Casimir effect demonstrates that the vacuum of space has a real, measurable energy density. This vacuum energy is one of the leading candidates for explaining the mysterious force known as dark energy, which is causing the expansion of our universe to accelerate. Yet here we encounter the greatest puzzle in all of physics. When theorists calculate how much energy this quantum foam should contain, based on the Casimir effect and other evidence, the number is astronomically, impossibly large, a 1 followed by 120 zeros larger than what we observe in the cosmological constant. This colossal discrepancy, known as the cosmological constant problem, is a glaring sign that something is profoundly wrong or missing in our union of quantum mechanics and gravity. The Casimir effect, therefore, is far more than a novel force. It is a window into the hidden heart of nothingness. It proves that the vacuum is not passive but active, not simple but structured. It suggests that what we perceive as empty space is in fact a dynamic medium, its energy potentially shaping the destiny of the entire cosmos. This forgotten breakthrough shatters our classical notion of emptiness, forcing us to accept that the void itself is a fundamental part of the universe's fabric, teeming with an invisible energy that may ultimately hold the key to understanding everything. Just when physicists were coming to terms with the bizarre reality that empty space is a seething ocean of quantum energy, another discovery emerged that challenged an even more fundamental assumption: what is truly real in the universe? For centuries, since the days of Michael Faraday and James Clerk Maxwell, the bedrock of electromagnetic theory had been the concept of fields. The electric field and the magnetic field were understood to be the real, physical entities that exerted forces on particles. They were the actors on the stage of physics. The electromagnetic potential, on the other hand, was seen as a mere mathematical convenience, a useful number you could plug into an equation to calculate what the fields were doing, but one that had no physical reality of its own. It was considered a helpful fiction, a kind of accounting tool with no deeper meaning. This was the settled, comfortable view. But in 1959, two physicists, Yakir Aharonov and David Bohm, turned this entire worldview on its head with a prediction so strange it seemed to defy logic itself. Their thought experiment was elegantly simple in concept, though devilishly complex in its quantum mechanical details. Imagine a beam of electrons, like a stream of tiny, identical particles, fired toward a screen. In its path, place a long, cylindrical solenoid, essentially a coil of wire that, when an electric current runs through it, creates a strong, donut-shaped magnetic field confined entirely inside the coil. Now, here is the crucial part. Outside this solenoid, the magnetic field is precisely zero. A sensitive compass placed there would not twitch. According to all classical physics, an electron traveling in this region of zero magnetic field should continue on its way completely unaffected, as if the solenoid weren't even there. It should be entirely oblivious to the magnetic activity happening inside the sealed coil. Aharonov and Bohm's quantum calculations, however, told a completely different and astonishing story. They predicted that the electrons passing outside the solenoid, in that region of perfect magnetic silence, would in fact be subtly influenced. The presence of the magnetic field inside the solenoid would somehow alter the behavior of the electrons outside it. More precisely, the electromagnetic potential associated with the solenoid, that supposedly mere mathematical abstraction, would change the quantum phase of the electron's wave function. This shift wouldn't change the electron's speed or energy, but it would alter its quantum interference pattern when it hit the detection screen. If you ran the experiment with the current off, you'd see one pattern of stripes. Turn the current on, and the entire pattern would shift sideways. The electrons were being ghostly manipulated by something that, according to all previous understanding, wasn't really there. They were feeling the influence of the electromagnetic potential directly, even in a region where its associated fields were completely absent. The physics community's reaction was a mixture of disbelief, skepticism, and in some quarters, outright dismissal. The idea was so counterintuitive it seemed to violate a basic principle of locality, the notion that an object can only be influenced by its immediate surroundings. How could an electron be affected by something from which it was completely isolated? It felt like magic. Critics argued there must be some flaw, some leaking field, or some misinterpretation of the quantum math. The potential had always been viewed as a mathematical scaffold used to build the real structure of the fields. Aharonov and Bohm were now claiming the scaffold itself had a physical reality, independent of the building. This was a heresy against the classical interpretation of electromagnetism, yet the relentless march of experiment would once again prove the power of a radical idea. Within a few years, researchers began devising ways to test this bizarre prediction. Refined experiments, first with electrons and later with other quantum systems, consistently confirmed the effect. The interference patterns did indeed shift exactly as Aharonov and Bohm had foretold. The electrons were responding to the potential itself. This was not a theoretical quirk, it was a hard, measurable fact of the quantum world. The Aharonov-Bohm effect forced a profound and humbling revision of what physicists consider to be physically significant. It demonstrated that the universe is not necessarily governed solely by the things we can directly measure, like force fields, but also by more abstract, non-local entities that lie beneath the surface. The implications of this forgotten breakthrough ripple far beyond a single curious experiment. It provided the first clear evidence that our classical intuitions, built on a world of billiard balls and force fields, are fundamentally inadequate for describing quantum reality. The effect is now considered foundational in quantum physics, forming the bedrock of our understanding of gauge theories, which are the framework for all modern particle physics, including the Standard Model. Furthermore, it is the fundamental principle behind the behavior of topological phases of matter, exotic states where electrons organize themselves in ways that are protected against local disturbances. This is the science behind the hope for fault-tolerant quantum computers. The Aharonov-Bohm effect teaches us a deep and subtle lesson about the architecture of reality, that the most fundamental truths may be hidden from direct view, expressed not in forces we can feel, but in abstract relationships and potentials that nonetheless weave the fabric of our world. It reveals a universe where influence is not always local, and where the most real things are sometimes the ones we cannot directly see. For years, the fierce debate between Einstein and Bauer over the EPR paradox remained just that, a philosophical debate, a war of words with no battlefield to settle it. It was a beautiful argument about the nature of reality, but one that seemed destined to remain forever in the realm of pure thought, untouchable by experiment. Both sides seemed equally unprovable. You could believe in Einstein's objective, local reality with its hidden variables, or you could believe in Bauer's spooky, interconnected quantum world, and your choice said more about your personal philosophy than it did about your science. The impasse was total, that is, until an unassuming physicist working at the European Organization for Nuclear Research, or CERN, decided to apply the cold, hard logic of mathematics to the problem. His name was John Stuart Bell, and in 1964 he performed a miracle of theoretical reasoning. He found a way to turn a metaphysical debate into an experimental recipe. He gave the world a concrete test, a way to ask the universe itself whether Einstein or Bauer was right. Bell's ingenious insight was to derive a set of mathematical inequalities. Now, that might sound dry, but its meaning was explosive. These Bell inequalities, as they became known, established a very specific limit, a boundary line that any universe described by Einstein's local hidden variables must obey. Imagine them as a speed limit on a cosmic highway. If Einstein was correct, and particles carried secret instructions from the moment they were born that predetermined their properties, then the statistical correlations between measurements on entangled particles could never exceed this speed limit. Their fates were linked at birth, so their behavior had to stay within a certain predictable, classical range. But quantum mechanics, in its typical bizarre fashion, laughed at this limit. The equations of Bauer, Heisenberg, and Schrödinger predicted that entangled particles would blow right past Bell's boundary. They would violate the inequalities, showing correlations that were stronger, faster, and more connected than any local, hidden variable theory could ever allow. Bell had constructed a perfect trap, run the experiment, and the result would tell you unequivocally who was right. If the measurements stayed within the limits, Einstein won and reality was local and deterministic. If they violated the limits, Bauer won and reality was non-local and inherently probabilistic. The beauty of Bell's theorem was its crystal clarity, but therein also lay the reason it was initially overlooked. The physics world of the 1960s was racing forward, building particle accelerators to smash matter into its constituents and landing people on the moon. Bell's paper was a deeply theoretical piece of work, a philosophical argument dressed in mathematical clothing. Furthermore, actually performing the experiment he envisioned was a monumental technological challenge. It required creating entangled particles, measuring their properties in perfect synchronization with randomly changing settings, and doing it all fast enough to ensure no light-speed signal could possibly communicate between the detectors, a feat far beyond the laboratory capabilities of the day. And so, Bell's magnificent theorem sat quietly, a time bomb of an idea ticking away in the pages of an academic journal, known only to a small circle of quantum foundation specialists. It was the ultimate solution in search of a problem, a key for a lock that hadn't yet been built. That lock would finally be forged nearly 2 decades later by a determined French physicist named Alain Aspect. In the early 1980s, Aspect and his team at the Institut d'Optique in Paris achieved what had once seemed impossible. They engineered an exquisitely precise experiment using pairs of entangled photons, particles of light. They could measure the polarization of these photons as they flew apart in opposite directions, and most crucially, they could change the angle of the measurement setting so quickly and randomly that there was absolutely no time for any hidden information to travel between the two sides. It was the perfect execution of Bell's thought experiment brought to life. The results were not ambiguous. The photons violated Bell's inequality by a wide margin. Their correlations were stronger than any local reality could possibly allow. The universe had answered the question. Bohr was right, Einstein was wrong. The impact of this confirmation was nothing short of revolutionary. It forced the entire physics community to accept a truth that many had found deeply uncomfortable. Nature is fundamentally non-local. Entangled particles do influence each other instantaneously across vast distances, a phenomenon we now call quantum non-locality. This doesn't allow for faster-than-light communication in a way that violates causality, but it does mean that the universe is wired together in a way that defies our classical billiard ball intuition. There is no hidden script. The particles aren't just revealing a plan made at their birth. They are engaging in a continuous, mysterious dance that connects them across space and time. Bell's theorem shattered the last hope for a return to a comfortable, deterministic cosmos. It ushered in the era of quantum information science, providing the essential bedrock for technologies like quantum cryptography and quantum computing, which are built on the very spookiness that Einstein so despised. John Bell's breakthrough stands as a towering testament to the power of pure thought. With nothing but pen, paper, and profound logical rigor, he devised a way to ask a question of the cosmos so precise that the answer would change our understanding of reality forever. If the nature of reality seemed strange and the nature of consciousness even stranger, what about the nature of time itself? Time is the most universal and intimate part of our experience. We feel it passing, we measure it, we mourn its loss, and we structure our entire lives around its relentless forward march. It seems as fundamental as anything could possibly be. But what if this most basic feature of existence is not fundamental at all? What if time is not a primary ingredient of the universe, but a secondary effect, an illusion that emerges from a deeper, timeless reality? This is the staggering, almost incomprehensible proposition at the heart of a forgotten breakthrough that came from the collaboration of two of the 20th century's greatest physicists, John Wheeler and Wheeler-DeWitt. In 1967, Wheeler and DeWitt set out to tackle the single greatest challenge in all of fundamental physics: uniting Einstein's theory of general relativity, which describes the force of gravity and the large-scale structure of spacetime, with quantum mechanics, which governs the bizarre world of the atom. These two pillars of modern physics are both spectacularly successful in their own domains, but they are utterly incompatible. Applying the equations of one to the realm of the other results in nonsensical answers and infinities. Wheeler and DeWitt's ambitious goal was to find a single, overarching equation that could describe the entire universe under one consistent set of rules, a theory of quantum gravity. The result of their labor was a deceptively simple-looking formula now known as the Wheeler-DeWitt Equation, but its implications were anything but simple. In fact, they were so radical that they seemed to erase one of the most basic elements of the cosmos from the ledger of fundamental things. When they applied the standard mathematical techniques of quantum theory to the entire universe, something bizarre happened. The variable for time simply vanished from their final equation. It disappeared completely. The Wheeler-DeWitt equation describes the state of the entire cosmos, but it does so in a way that is completely static. There is no T for time in it. It portrays a universe that just is, a frozen, unchanging block of reality. In this view, the Big Bang, the formation of stars, the rise and fall of civilizations, and every event in history are not unfolding in a temporal sequence. They are all equally real and present, like fixed points on a vast, timeless map. The equation suggests that time is not a fundamental dimension in which the universe evolves. Instead, it might be an emergent property, a useful illusion that arises from the complex correlations between quantum events within the universe, much like the sensation of temperature emerges from the frantic jiggling of atoms, even though no single atom has a temperature itself. To grasp how bewildering this idea was, consider a movie on a DVD. The entire film, from opening credits to final scene, is encoded on the disc all at once. It is complete and static. The experience of watching the movie, the flow of time, the narrative, the cause and effect, is not a property of the disc itself. It emerges when the disc is played, when the laser reads the information in a specific sequence and a viewer perceives it. The Wheeler-DeWitt equation treats the universe like that DVD. The entire history and future are encoded in a single, timeless quantum state. Our conscious experience of living moment to moment is like the laser moving across the disc, creating the illusion of a flowing present from a static whole. Unsurprisingly, this concept of a timeless universe was met with a combination of confusion, skepticism, and outright dismissal by the wider physics community. The idea was so counter to every human intuition and every successful theory before it that it was largely set aside as a mathematical curiosity, a peculiar artifact of an incomplete theory. How could one reconcile this frozen, static picture with our direct, undeniable experience of time's flow? The equation became famous as the ultimate example of a theory being unable to cook. As one critic put it, it could describe the ingredients of the universe, but it couldn't explain the process of baking. For decades, it languished on the intellectual shelf, a profound but seemingly impractical dead end. Yet, the power of a truly profound idea is its refusal to stay forgotten. In recent years, the timeless nature of the Wheeler-DeWitt equation has experienced a dramatic revival, finding new life and new interpretations within cutting-edge approaches to quantum gravity. Theories like loop quantum gravity and various formulations of string theory have begun to take the idea of emergent time very seriously. They are exploring how the familiar, flowing time of our daily experience might be reconstructed from more primitive, timeless building blocks. In these modern views, time could emerge from the quantum entanglement between different parts of the universe, or from the sheer complexity of the cosmos's quantum state. The flow of time might be analogous to the perception of down for a person on Earth. Down isn't a fundamental force of the universe, it's a compelling illusion created by the local effects of gravity. In the same way, now might not be a fundamental property of the cosmos, but a powerful perceptual phenomenon generated by our particular vantage point within a timeless whole. The work of Wheeler and DeWitt ultimately challenges us to perform a breathtaking feat of intellectual humility. It asks us to consider that our most basic experience of reality, the relentless tick of the clock, the feeling of the past receding and the future approaching, might be a kind of user interface, a simplified way for our consciousness to make sense of a universe that is, at its most fundamental level, complete and eternal. It suggests that change itself may be a kind of reading of a timeless text, and that the true nature of reality is a still and silent ocean, of which our flowing stream of time is but a surface wave. But if the timeless universe of Wheeler and DeWitt felt abstract, the next forgotten breakthrough would make the very space around us feel equally illusory. For centuries, we have navigated the world with an unshakable belief in its three-dimensional solidity. The depth of a canyon, the volume of a room, the vast expanse between stars, these all feel undeniably real. But what if this rich, three-dimensional experience is nothing more than a magnificent projection, a cosmic mirage? This is the mind-bending proposition at the heart of the holographic principle, an idea so radical that it emerged not from a desire to explain space, but from a desperate attempt to solve a paradox at the edge of nothingness, the event horizon of a black hole. The story begins in the 1970s when a young physicist named Jacob Bekenstein made a startling calculation. He proposed that a black hole must have entropy. This was a shocking notion because entropy is a measure of disorder or information content, typically applied to systems like gases or engines. A black hole, according to classical general relativity, was supposed to be the simplest object in the universe defined only by its mass, spin, and charge. It was a vacuum cleaner for information, sucking everything in and leaving no trace. Bekenstein's idea suggested the opposite, that a black hole wasn't a destroyer of information but a storehouse of it, and that the amount of information it could hold was not proportional to its volume, but to the area of its event horizon. Stephen Hawking initially scoffed at the idea, but soon his own work on Hawking radiation would confirm that black holes do indeed have entropy and a temperature, cementing this bizarre link between information, gravity, and geometry. This discovery, known as the Bekenstein-Hawking Formula, planted a seed. It implied that all the information needed to describe everything that had ever fallen into a black hole, every atom, every photon, every page of every book, was not lost inside its unknowable depths, but was somehow encoded on its two-dimensional surface, the event horizon. The entire three-dimensional interior of the black hole could be described by bits of information painted on its boundary. It was as if the content of a vast three-dimensional library was completely captured by the text written on its two-dimensional walls. This was the crucial, perplexing clue. In the early 1990s, two towering figures in theoretical physics, Gerard T. Hooft and Leonard Susskind, took this clue and ran with it, pushing the idea to its logical and astonishing extreme. If it was true for a black hole, they asked, why couldn't it be true for the entire universe? What if our whole cosmos operates on the same principle? They formally proposed the holographic principle, suggesting that all the information contained within any volume of space, including the room you're in right now, or the entire observable universe, can be fully described by bits of information stored on its surrounding boundary. In this view, our perceived three-dimensional reality is a projection, a hologram emanating from a vast, complex, two-dimensional surface at the edge of space. We are not living in the hologram, we are the hologram. The solidity of your desk, the depth of the sky, the feeling of your own body, all of it is an incredibly convincing, three-dimensional translation of a cosmic code written on a distant, two-dimensional screen. Unsurprisingly, the initial reaction from much of the physics community was a mixture of bewilderment and outright rejection. The principle seemed to violate cherished notions of locality, the idea that objects can only be directly influenced by their immediate surroundings. It felt like saying the story of a novel is not contained in its words, but is instead somehow encoded on the edges of its pages. It was counterintuitive to the point of seeming nonsensical. How could a flat surface possibly contain the information for a volumetric world? The principle was seen as a provocative metaphor, perhaps useful for black hole physics, but certainly not a literal description of our everyday reality. The skepticism began to crumble just a few years later, in 1997, when a young Argentinian physicist named Juan Maldacena provided a stunning mathematical realization of the holographic principle. He discovered what is now known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. In a monumental breakthrough, Maldacena showed that a theory of gravity operating in a hypothetical five-dimensional space, a bulk, was completely equivalent to a quantum field theory without gravity operating on its four-dimensional boundary. It was a precise mathematical dictionary translating the language of strings and gravity in a higher dimension into the language of particles and forces on a lower dimensional surface. This was no longer just a suggestive analogy, it was a concrete, calculable duality. The holographic principle had found its first rigorous footing, transforming from a wild speculation into a serious framework for unifying gravity and quantum mechanics. The implications of this are so profound they are difficult to overstate. It suggests that gravity, the force that shapes the cosmos, might not be a fundamental force at all, but an emergent phenomenon. Just as the sensation of wetness emerges from the collective behavior of countless water molecules, gravity might emerge from the complex interactions of information on the universe's boundary. What we perceive as the warping of spacetime by mass could simply be a shadow, a holographic consequence of quantum processes happening on a distant surface we can never see. This turns our entire conception of reality inside out. The universe is not a container for information. The universe is information. The stuff of reality is not matter and energy, but bits and bytes. The cosmos is not a physical machine. It is a cosmic computation, a vast and ongoing calculation whose output is the breathtakingly realistic, three-dimensional world we experience every day. The holographic principle, once a forgotten and heretical idea, now stands as one of the most promising paths toward a complete theory of quantum gravity, forcing us to accept that the ultimate nature of reality may be far more alien and wondrous than our three-dimensional senses could ever perceive. So if the holographic principle suggests our reality is a projection from a cosmic code, a profound question still remains. Why does this projected world feel so solid, so definite, and so consistent to all of us? In the quantum realm, particles exist in ghostly superpositions, being in multiple states at once until measured. Yet we never see a cat that is both dead and alive, or a table that is both here and there. Our everyday experience is stubbornly, reliably classical. This is the infamous measurement problem, and for decades, the leading explanations felt deeply unsatisfying, either invoking a mysterious collapse of the wave function or an infinite number of splitting universes. But at the turn of the millennium, a physicist at Los Alamos National Laboratory named Wojciech offered a breathtakingly elegant and natural solution. He called it quantum Darwinism, and it proposes that the definite reality we all agree upon emerges through a process strikingly similar to biological evolution, environmental selection. Jacques' central insight was to stop asking what causes the quantum wave function to collapse, and instead ask why we all see the same collapsed outcome. He realized that for you and I to both agree that a chair is in a specific location, information about that chair's location must be widely available. It has to be copied, broadcast, and accessible to anyone who looks. In the quantum world, this doesn't happen for every possible state. A fragile quantum superposition is like a secret whispered to a single friend. It's delicate and easily lost. But a robust classical state is like a headline blasted across the internet. It's copied countless times, making it durable and available to everyone. Jacques proposed that the environment itself acts as a kind of information copying machine. When a quantum system interacts with the countless particles in its surroundings, photons of light, molecules of air, the dust in the room, information about its state gets imprinted onto these environmental particles. But here's the crucial evolutionary twist. Not all quantum states are created equal. Some states are far more robust and stable when interacting with the environment. These are known as pointer states, and they are the ones that can be copied over and over again without being drastically altered or destroyed. They are the quantum equivalent of a species perfectly adapted to its niche. Other, more fragile superpositions are quickly decohered. Their quantum magic is scrambled and wiped away by the constant bombardment from the environment. They simply cannot survive the process of being observed and copied. In this way, the environment acts as a selective pressure, weeding out the fragile superpositions and allowing only the most stable, robust states to proliferate. These winning states are then selected for by having their information copied into thousands, millions, or even billions of fragments in the environment. This is the Darwinism in quantum Darwinism. The reality we perceive is not a single, absolute collapse. It is the consensus reality formed by the states that have been most successfully replicated and disseminated throughout our shared environment. When you walk into a room and see a chair in the corner, you are not directly perceiving the chair itself. You are catching glimpses of the countless photons of light that have bounced off it, each one carrying a tiny, redundant copy of the information. Chair is here. So is every other person in the room. We all independently access the same widely available data, and that is why we all agree on the chair's position. The chair's location has achieved what Jacques calls objective reality, not because it exists independently of observation, but because it has been so thoroughly observed and recorded by the environment that it becomes impossible for any observer to see anything else. The quantum possibilities have not vanished, they have simply been outcompeted. The winning state has left so many informational offspring that it dominates our perception completely. Initially, this theory was a niche idea, a fascinating thought experiment that required physicists to make a significant shift in perspective. It moved the focus from the isolated quantum system to the entire ecosystem of the system and its environment. It asked them to think about information as a tangible currency that flows and replicates. For a field steeped in the traditions of either Bauer's Copenhagen interpretation or Everett's many worlds, this third path was novel and somewhat overlooked. However, in recent years, advanced experiments in quantum information have begun to put quantum Darwinism to the test. Researchers are now able to create tiny, controlled quantum systems and carefully monitor how information about their states leaks into a simulated environment. The results so far are remarkably supportive. They show that certain states do indeed become amplified as they are redundantly copied into the environment, while superpositions are rapidly erased. We are literally watching classicality emerge from the quantum fog through a process of natural selection. Jacques' forgotten breakthrough offers a powerful and deeply elegant resolution to one of physics' oldest puzzles. It tells us that the world appears solid and objective, not because of a mysterious collapse triggered by consciousness, but because of a practical, selective process of information broadcasting. Reality is not dictated by a single observer, but emerges from a consensus reached by the environment itself. The stable, predictable world we experience is simply the set of quantum states that were fit enough to survive, replicate, and become the shared story we all tell ourselves about the universe. It is a story written not by a single author, but by the relentless and selective copying of nature itself. Just when we think we've explored every possible corner of quantum weirdness, from multiple worlds to holographic projections, another idea emerges that is so radical it seems to bend the very fabric of causality itself. What if the strangest feature of the quantum world isn't its uncertainty or its interconnectedness, but its relationship with time? We are all bound by an unshakable intuition that time flows in one direction only, from the past, through the present, and into the future. Cause must always precede effect. This linear arrow of time is woven into the very core of our experience, our language, and our laws of physics. But in 1986, a physicist at the University of Washington named John Cramer dared to ask a heretical question. What if that's just an illusion? What if, at the quantum level, the future can reach back and shake hands with the past? His answer was the transactional interpretation of quantum mechanics, a theory that doesn't just tweak our understanding of particles, but completely upends our conception of time itself. Cramer's inspiration came from a curious feature of the mathematical equations that describe quantum waves. These equations, developed by Paul Dirac and others, often have two solutions, one that describes a wave moving forward in time, and another that describes an identical wave moving backward in time. For decades, physicists had treated this second solution as a meaningless mathematical artifact, an inconvenient quirk to be ignored. After all, everyone knew waves couldn't actually travel backward in time. Cramer, however, took this discarded solution seriously. He proposed that both waves are real. In his transactional interpretation, every quantum event begins with an emitter, say, an atom sending out what he called an alpha wave. This wave propagates forward in time, spreading out through space and exploring all possible paths, just as in the standard quantum theory. But here's the revolutionary part. This alpha wave eventually reaches a receiver, perhaps a detector screen or another particle. Upon arrival, the receiver then sends a confirmation wave backward in time, directly back along the same path to the original emitter. It's like sending out an invitation and getting an RSVP that travels back through time to confirm the arrangement the moment it was sent. The actualized event, the click of a detector, the appearance of a dot on a screen, only occurs when these two waves, the alpha wave moving forward and the confirmation wave moving backward, meet and form a closed loop in time. Cramer called this handshake across time a transaction. It is this transaction that collapses the wave function and creates a definite reality. This elegant mechanism provides a stunningly simple explanation for one of quantum mechanics' oldest puzzles, the double-slit experiment. In this classic setup, a single electron seems to pass through two slits at once, interfering with itself to create a pattern of stripes. The standard interpretation says the electron is in a superposition until measured, but can't explain how it knows to create an interference pattern. The many worlds interpretation says it goes through both slits in different universes. Cramer's interpretation offers a different view. The alpha wave from the electron goes through both slits, exploring all paths. The confirmation wave from the detector screen then travels back through time, selectively reinforcing only those paths that will constructively interfere to form the final pattern. The electron doesn't choose a path. The future detector helps it choose by sending confirmation back to the past. Unsurprisingly, the physics community reacted to this idea with a mixture of fascination and profound discomfort. The primary objection was its reliance on retrocausality, the notion that an effect, the confirmation wave, can precede its cause, the emission of the offer wave. This violates not only our everyday intuition but a foundational principle of classical physics. Critics argued it opened the door to insurmountable paradoxes, like the infamous grandfather paradox, where someone could go back in time and prevent their own birth. Kramer countered that the transactional interpretation is inherently consistent and paradox-free. The confirmation waves, he argued, can only reinforce what has already been initiated. They cannot create entirely new events out of nothing. You can't send a confirmation wave for a transaction that was never offered. The loop is sealed and self-consistent. Despite this logical defense, the idea of backward time travel, even on a quantum scale, was simply too radical for most researchers to accept. The interpretation was largely dismissed as a clever but fanciful metaphor with no experimental consequences, another interesting but ultimately untestable idea relegated to the footnotes of quantum foundations. Yet, like a confirmation wave itself, interest in Kramer's work has echoed back from the future. In recent years, the transactional interpretation has experienced a quiet but significant revival, finding new relevance in two cutting-edge areas. First, in the realm of quantum foundations, it provides a unique and compelling solution to the measurement problem without needing wave function collapse or an infinity of branching worlds. It offers an objective physical mechanism for how probabilities become actualities. Second, and perhaps more practically, it has influenced the field of quantum communication. The idea of two-way communication between sender and receiver, even if metaphorical, has inspired new protocols for quantum key distribution and other secure communication methods, leveraging the unique handshake nature of quantum events. The most profound implication of Kramer's forgotten breakthrough is that it forces us to reconsider time not as a flowing river, but as a static ocean. In the transactional view, the past, present, and future are all equally real and exist in a fixed relationship. A quantum transaction is a loop that connects them all into a single, timeless event. This suggests that our linear experience of cause and effect may be a macroscopic illusion, an emergent property of a world where countless quantum transactions are averaging out to create an arrow of time. John Kramer's work stands as a powerful reminder that our most deeply held assumptions about reality, especially the nature of time, may be the very things holding us back from a deeper understanding. It challenges us to consider that the universe might not be a story unfolding in a sequence of moments, but a vast, interconnected tapestry where every event is linked to every other, not just through space but through time as well. For decades, the standard model of cosmology has presented a comforting, almost serene picture of our universe's infancy. It tells us that the cosmos began in a hot, dense state with the Big Bang and then expanded and cooled, leaving behind a nearly perfect fossil glow, the cosmic microwave background radiation. This afterglow, bathing the entire universe, is supposed to be remarkably uniform, a testament to a young cosmos that was smooth and homogeneous, with only tiny, random fluctuations that would one day seed the galaxies. It's an elegant, powerful story, one that has become the bedrock of modern cosmology. But what if this foundational image, this baby picture of the universe, contains a few unexpected and deeply puzzling blemishes? What if, upon closer inspection, the early universe was not perfectly uniform, but showed signs of a more complex and asymmetric origin. This is the startling possibility raised by the most detailed map of the cosmic microwave background ever created, produced by the European Space Agency's Planck satellite in 2013. Its exquisite data didn't just confirm the standard model, it also revealed a handful of stubborn, curious anomalies that refused to go away, tiny cosmic wrinkles that could be the first hints of a reality far stranger and more vast than we ever imagined. The most significant of these Planck anomalies is a dramatic large-scale asymmetry, often called the axis of evil by researchers. Imagine the entire sky as a sphere. According to the standard model, the temperature fluctuations in the cosmic microwave background should be distributed completely randomly, like static on an old television screen. There should be no preferred direction, no special axis, but the Planck map showed something different. The fluctuations in one half of the sky are noticeably stronger and more pronounced than those in the opposite half. It's as if the universe has a lopsided face with one cheek warmer than the other. This isn't just a minor statistical quirk, it's a fundamental challenge to the principle of isotropy, the idea that the universe looks the same in every direction, which is a cornerstone of the standard cosmological model. Finding a preferred axis in the cosmos is like discovering that a supposedly perfectly round ball actually has a distinct top and bottom. It forces us to question the very assumptions we use to mold it. Then there is the infamous cold spot. This is a particularly large and unusually cold region in the cosmic microwave background, a vast circular area where the temperature is significantly lower than the surrounding average. While the sky is full of hot and cold spots, this one is a true outlier, a statistical anomaly so large that it's very difficult to explain as a simple random fluctuation. It's like rolling a die 1,000,000 times and getting a sequence of 100 sixes in a row. It's not technically impossible, but it strongly suggests that the die might be loaded. Some cosmologists have proposed that the cold spot isn't a feature of the early universe at all, but rather a shadow cast by a gigantic cosmic void, an immense emptiness in the distribution of galaxies between us and the cosmic microwave background. Yet, even this exotic explanation has its problems, as the required void would be so absurdly large that it would itself challenge our understanding of how structure forms in the universe. The initial reaction from much of the cosmological community was one of cautious skepticism, often leaning toward dismissal. The standard model, known as the lambda cold dark matter model, has been spectacularly successful in explaining a huge range of observations. When faced with a few stubborn data points that don't fit, the natural inclination is to assume they are merely statistical flukes, ghosts in the machine that will vanish with more precise data or better analysis. Many researchers argued that we were simply seeing patterns in the noise, a form of cosmic pareidolia not unlike seeing a face in the clouds. This is a perfectly reasonable and scientifically conservative approach. After all, extraordinary claims require extraordinary evidence, and a few anomalies in a sea of confirming data are not enough to overthrow a well-established paradigm. However, the persistence of these anomalies, even in the final, most refined data release from Planck, has prevented them from being easily swept away. Their existence has become a fertile ground for theorists willing to venture beyond the standard model, offering thrilling new possibilities that were once confined to the realm of pure speculation. One of the most profound interpretations is that these asymmetries are not flaws in the data, but cosmic scars, evidence that our universe collided with another universe in the distant past. In the theory of eternal inflation, our Big Bang is not a unique event, but merely one bubble nucleating in an endless, frothing multiverse of inflating space. As these bubbles expand, they could occasionally bump into each other. Such a collision would leave an indelible imprint on the cosmic microwave background of both universes, potentially creating a region of asymmetry or a strange cold spot exactly like the one we see. The Planck anomalies, in this view, could be our first ever empirical evidence for the existence of other universes, a breathtaking glimpse into a multiverse that is infinitely larger and more varied than our own cosmic bubble. Another radical idea comes from Nobel laureate Sir Roger Penrose's conformal cyclic cosmology. This theory proposes that the universe is not a one-time event, but goes through endless cycles of expansion, death, and rebirth. In this model, the distant future of our universe, a cold, empty expanse dominated by black holes that have evaporated away, becomes the Big Bang of the next eon. Penrose suggests that the energy released by the evaporation of supermassive black holes in the previous eon could imprint itself as concentric rings of temperature variation in the cosmic microwave background of the next one. Intriguingly, some researchers claim to have found evidence of exactly such patterns in the Planck data, centered on the cold spot itself. If true, this would mean the cold spot is not a void or a collision, but a ghostly echo from a universe that existed trillions of years before our own, a cosmic memory encoded in the first light of creation. Whether they are ultimately confirmed as real or explained away as errors, the Planck anomalies serve a crucial purpose. They are a vital reminder that our current models, however successful, are almost certainly incomplete. They are the tantalizing loose threads at the edge of our cosmological tapestry, pulling on which could unravel our current understanding and reveal a much richer, more complex, and far more wondrous picture of reality. They encourage us to be humble, to question our assumptions, and to keep looking deeper, because the greatest discoveries often lie hidden in the details we initially dismiss as mere noise. Stephen Hawking's brilliant mind had already reshaped our understanding of black holes by showing they weren't completely black, but could radiate energy and slowly evaporate. Yet this very discovery led him to a terrifying conclusion, one that threatened to unravel the entire logical foundation of physics. He realized that if a black hole evaporates completely, every single bit of information about what fell into it, every atom, every photon, every page of every book, would be irretrievably lost to the universe, erased from existence. This became known as the black hole information paradox, and it struck at the heart of science itself because it violated one of the most sacred principles of quantum mechanics, the law of information conservation. In the quantum world, information is never truly destroyed. It might be scrambled, transformed, or hidden, but in principle, it is always preserved. If you could somehow reverse all the motions of every particle in a cloud of smoke, you could theoretically reconstruct the original log that burned. This reversibility is encoded in the quantum mechanical equations, but Hawking's calculations suggested that black holes were the ultimate cosmic shredders. They take the intricate, ordered information of stars, planets, and spaceships and transform it into a featureless, random bath of thermal radiation, Hawking radiation, that contains no trace of what created it. The input is a unique, complex history. The output is a bland, generic hum of heat. If this were true, it would mean the universe has a fundamental amnesia, that history itself can be erased, and the deterministic laws of physics would break down at the edge of a black hole. This was so unsettling that even Hawking himself initially believed it meant quantum mechanics would need to be rewritten. The physics community was thrown into an uproar that has lasted for decades. On one side were those who, like Hawking, felt that information loss was a necessary consequence of his radiation. On the other were defenders of quantum orthodoxy, most notably Leonard Susskind, who argued that information must be preserved even if we don't yet understand how. This wasn't just an academic debate. It was a battle over the nature of reality, fought through heated arguments and a famous bet between Hawking and Susskind that Hawking eventually conceded. The search for a solution gave birth to some of the most radical ideas in modern physics. The holographic principle emerged as a leading contender, suggesting that information isn't lost because it was never actually inside the black hole to begin with. Instead, it's perfectly encoded on the event horizon, the black hole's two-dimensional surface, like a cosmic DVD storing the data for a three-dimensional movie. Later, the idea of black hole complementarity proposed that from the perspective of an outside observer, the information is smeared on the horizon, while for someone falling in, it passes through untouched, a strange duality where both stories are true in their own reference frames. More recently, the debate took an even wilder turn with the proposal of the firewall paradox. If information is to be returned via Hawking radiation, the argument goes, it might require a literal wall of unimaginably high-energy particles waiting at the event horizon, instantly incinerating any astronaut daring to cross. This violent solution was proposed to save quantum mechanics, but it would utterly destroy Einstein's general relativity, which insists that crossing an event horizon should be an unremarkable, smooth experience. For a time, it seemed physicists had to choose between blowing up Einstein's principle of equivalence or accepting that information was lost and quantum mechanics was flawed, a true crisis. For years, this furious debate was purely theoretical, a war of equations on blackboards with no way to test who was right, but that is beginning to change. The rise of quantum computing and advanced gravitational wave astronomy is providing new tools to probe these ideas. Researchers are now designing thought experiments that could be tested with sophisticated quantum simulators, looking for signatures of how information might scramble and escape. The study of quantum entanglement itself is key, with discoveries like the ER=EPR conjecture suggesting that entangled particles might be connected by microscopic wormholes, providing a hidden pathway for information to travel. Every time two black holes merge and send ripples through spacetime detected by LIGO and Virgo observatories, we are gathering data that could hold clues about the behavior of event horizons and the information they contain. Stephen Hawking himself eventually changed his mind, suggesting late in his life that information might indeed be preserved, perhaps encoded in the Hawking radiation itself in a complex and subtle way. The resolution of this paradox is about far more than the fate of what falls into a black hole. It is the essential key to unlocking a theory of quantum gravity, the holy grail of modern physics. The conflict exposes the deep incompatibility between our two most successful theories, the smooth, geometric reality of general relativity and the discrete, informational reality of quantum mechanics. Whichever theory yields to resolve the paradox will tell us what is more fundamental, the geometry of spacetime or the information it contains. Hawking's paradox forces us to confront the astonishing possibility that information is not just something we can know about the universe, but the very substance from which the universe is woven. In this view, particles, forces, and even space and time might be secondary phenomena, emergent properties of a deeper, more abstract layer of reality built from pure information. The cosmos might not be a physical machine but a cosmic computation, and black holes are its ultimate test. While the holographic principle offered a stunning metaphor, a vision of our universe as a cosmic projection, it remained just that for many, a powerful but abstract idea, more philosophy than hard physics. How could a two-dimensional surface possibly encode the rich, three-dimensional reality we experience, the principle cried out for a concrete mathematical foundation, a precise dictionary to translate between the world of the boundary and the world of the bulk. In 1997, a young physicist at Harvard named Juan Maldassner provided exactly that, and in doing so, he gave the world one of the most profound and far-reaching breakthroughs in modern theoretical physics, the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT. Maldassner's discovery emerged from his work on string theory, an ambitious framework that proposes the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. He was studying the behavior of these strings in a hypothetical type of universe known as anti-de Sitter space. Unlike our own universe, which is expanding at an accelerating rate, anti-de Sitter space is negatively curved, exerting a kind of gravitational pull that causes it to act like a sealed cosmic box with a distinct boundary. Within this box, Maldassner was examining a complex setup involving both strings and higher dimensional membranes. Through a series of brilliant mathematical insights, he realized that this entire complicated gravitational system, with its strings moving through a warped, multi-dimensional space, was completely equivalent to a very different kind of theory operating only on the boundary of that space. This boundary theory was a conformal field theory, a particular type of quantum field theory that lacks any fixed scale and is perfectly symmetric under stretching and shrinking. The sheer audacity of this correspondence is difficult to overstate. On one side of the duality, you have a theory of quantum gravity operating in the multi-dimensional bulk of this hypothetical universe. This theory includes black holes, warped spacetime, and all the bizarre phenomena predicted by general relativity. On the other side, you have a quantum field theory living on the lower dimensional boundary of that universe. This boundary theory has no gravity at all. It describes particles and forces interacting on a fixed, rigid stage, much like the standard model of particle physics, but with a specific high degree of symmetry. Maldassner had found a perfect one-to-one dictionary. Every single phenomenon in the gravitational bulk, every particle, every gravitational wave, every black hole collision, has a unique, equivalent description as a complex interaction of particles on the boundary. A calculation that is impossibly difficult in the gravity theory might be straightforward in the field theory, and vice versa. It was the first rigorous mathematical realization of the holographic principle. The three-dimensional interior of this universe was indeed a perfect projection of a two-dimensional quantum code written on its outer shell. Initially, many in the physics community viewed AD-S/CFT as a fascinating mathematical curiosity, a neat trick that worked only in the rarefied and unrealistic environment of anti-de Sitter space. After all, we live in a universe that appears to be accelerating its expansion, not one with a confining boundary, but the power and beauty of the correspondence were too great to ignore. Researchers quickly realized that this was far more than a technical tool. It was a paradigm-shifting lens through which to view some of physics' most intractable problems. For the first time, it provided a solid framework to study quantum gravity using the well-established language of quantum field theory, a process as mysterious as the evaporation of a black hole, which involves puzzling quantum gravitational effects, could be translated into a problem involving the thermalization of particles in a hot plasma on the boundary, a problem physicists knew how to solve. This has led to stunning insights into the behavior of quark-gluon plasmas, the super-hot soups of matter created in particle accelerators like the Large Hadron Collider, and has even shed light on the strange properties of exotic materials like high-temperature superconductors. The most profound implication of Maldaisner's work is its radical suggestion about the nature of gravity itself. In the AD/S/CFT correspondence, gravity in the bulk is not a fundamental force. It emerges from the complex, entangled interactions of the quantum particles living on the boundary. Think of it like the phenomenon of temperature. A single molecule doesn't have a temperature. Temperature is a collective property that emerges from the frantic motion of trillions of molecules. In the same way, AD/S/CFT suggests that the force of gravity and the very fabric of spacetime it bends might be collective, emergent properties arising from a vast network of quantum information exchange. The space we move through and the gravity we feel may be a kind of illusion, a holographic mirage generated by a vast, complex quantum system operating on a distant surface we can never see. This turns our entire conception of reality on its head. We are no longer living in a space-time arena. We are a manifestation of a quantum process, and the arena itself is part of the show. Maldaisner's correspondence challenges our deepest notions of what is fundamental in the universe. It presents us with a genuine duality, two completely different descriptions of reality that are nonetheless mathematically equivalent. Is the true reality the one with gravity and curved spacetime, or is it the one with quantum particles interacting on a flat screen? The breakthrough suggests this might be a false choice, that both descriptions are equally valid, and fundamentality itself may be a perspective-dependent concept. This discovery, born from the abstract world of string theory, has become a cornerstone of modern theoretical physics, a gift that keeps on giving. It demonstrates with breathtaking clarity that deep, hidden symmetries in the laws of nature can reveal layers of reality that are completely unexpected, showing us that the universe is far more interconnected, mysterious, and elegant than we ever dared to dream. Just when we thought our picture of reality couldn't get any more abstract with holograms, emergent time, and cosmic codes, a pair of physicists unveiled a discovery that strips away yet another layer of the familiar, suggesting that even space and time themselves might be little more than useful illusions. In 2013, Nima Arkani-Hamed and Jaroslav Terenkeje introduced the world to a bizarre and beautiful geometric object called the Amplitudehedron. This multi-dimensional shape isn't just a mathematical curiosity. It's a revolutionary computational engine that has upended our understanding of how particles interact, and in doing so, has hinted that the very stage of reality might be built from something far more fundamental than spacetime. To grasp why the Amplitudehedron is so revolutionary, we have to understand the monumental task physicists face every day. The primary tool for calculating what happens when particles collide, like at the Large Hadron Collider, is a framework known as quantum field theory, and its mathematical engine is a notoriously complex and tedious process called Feynman diagrams. Developed by the legendary Richard Feynman, these diagrams are a way to visualize and calculate the probabilities of every possible way particles can interact and exchange force-carrying particles. The problem is, for even a simple collision, you have to draw thousands upon thousands of these diagrams, each representing a different path the particles could take, and then add them all up. The calculations are so laborious that they can take years, and they rely on two sacred principles that have been the bedrock of physics for a century: locality and unitarity. Locality is the idea that objects can only be directly influenced by their immediate surroundings, not by things far away. Unitarity is the guarantee that the probabilities of all possible outcomes of any quantum event must add up to 100% essentially, the assurance that nothing is lost or created from nothing in the equations. These principles are so fundamental that they feel like non-negotiable aspects of reality itself. but Aharonov-Bohm and Theorem made a stunning discovery. They found that for a wide class of particle interactions, they could calculate the outcomes with breathtaking speed and elegance by simply finding the volume of this strange new geometric shape, the amplituhedron. And the most shocking part, their method completely bypassed the need for Feynman diagrams. It didn't use locality, it didn't use unitarity, it didn't even use quantum mechanics in the traditional sense. The answers just fell out of the geometry, as if the universe had been using a needlessly complicated calculator all this time when the answer was already written in the shape of a perfect crystal. This was more than just a clever mathematical shortcut. It was a profound clue about the architecture of reality. The fact that the amplituhedron could reproduce the results of quantum field theory without referencing locality or unitarity suggests that these principles might not be fundamental laws of the universe. Instead, they might be emergent properties, side effects that fall out of a deeper, more primitive geometric reality. Think of it like the sensation of wetness. Water isn't fundamentally wet. Wetness is a property that emerges from the collective behavior of countless H2O molecules. In the same way, locality and unitarity, and by extension, space and time themselves, might not be the foundation of the cosmos. They could be phenomena that emerge from the underlying geometric relationships described by the amplituhedron. The implications of this are staggering. It suggests that the universe at its most fundamental level might not be made of particles vibrating in fields within a spacetime arena. It might be made of pure, timeless, and spaceless mathematics. The collisions we see in particle accelerators, the forces we feel, and the very dimensions we move through could all be a shadow cast by the intricate, multi-dimensional geometry of objects like the amplituhedron. Physics, in this view, becomes a secondary effect. The primary reality is mathematical and geometric. We are not living in a universe described by mathematics. We are living in a universe that is mathematics. Initially, many in the physics community viewed the amplituhedron as a powerful but highly specialized technical tool, a welcome relief for those doing grueling calculations, but not necessarily a paradigm-shifting idea. It was explored in a specific, simplified type of quantum field theory, and it wasn't immediately clear if it could be generalized to describe the messy, complex reality of our actual universe, complete with gravity. But the seed had been planted. The amplituhedron has since sparked a renaissance in how physicists think about the nature of reality, inspiring them to ask if all of physics might be reconstructed from similar combinatorial geometric principles. It has become a beacon for those seeking a theory of quantum gravity, suggesting that the way to unite gravity with the quantum world is not to quantize spacetime, but to find the geometric object from which both spacetime and quantum mechanics simultaneously emerge. Aharonov-Bohm himself has passionately argued that the amplituhedron points toward a future, post-spacetime physics. He encourages us to imagine a cosmos where space and time are not the starting point but the end result-derived concepts that only appear when we, as macroscopic observers, interact with this deeper mathematical structure. This geometric vision of reality is both humbling and exhilarating. It tells us that the world of tangible objects and definite locations is a simplified interface, a user-friendly projection of a reality that is far more alien, more beautiful, and more fundamentally mathematical than we ever conceived. The amplituhedron doesn't just calculate particle interactions. It invites us to consider that the entire universe might be a sublime piece of geometry, and that we are within it. If the holographic principle showed us that reality might be a projection, and the amplituhedron hinted that spacetime is emergent, then what is the actual thread from which the fabric of the cosmos is woven? The answer may lie in one of the most profound and poetic ideas to emerge from theoretical physics in the last decade, a concept that connects the weirdness of the quantum world directly to the warped geometry of gravity. In 2013, building on the monumental success of his AD/S/CFT correspondence, Juan Maldacena joined forces with the legendary Leonard Susskind to propose a breathtaking conjecture that can be summarized in a deceptively simple equation: ER equals EPR. This elegant formula is a bridge between two of Einstein's greatest intellectual achievements that have long been thought to be completely separate. On the left side, ER stands for Einstein-Rosen bridges, the formal name for what we commonly call wormholes, theoretical tunnels through spacetime that could, in principle, connect two distant points in the universe. On the right side, EPR stands for the famous paradox conceived by Einstein, Podolsky, and Rosen, the very thought experiment that first introduced the world to the spooky phenomenon of quantum entanglement. For decades, these two ideas lived in entirely different neighborhoods of physics. Wormholes were the stuff of general relativity, solutions to Einstein's equations that described the bending of spacetime itself. Entanglement was the heart of quantum weirdness, a bizarre connection between particles that seemed to have nothing to do with geometry. They were considered unrelated, even contradictory. Susskind and Maldacena's radical proposal was that they are not just similar, they are exactly the same thing. An entangled pair of particles, they suggested, is not simply linked by some invisible, instantaneous action. They are literally connected by a microscopic wormhole, a tiny, Planck-scale bridge in the fabric of spacetime itself. To understand how revolutionary this idea is, imagine two electrons created together so that their properties become inextricably linked or entangled. In the standard quantum view, if you separate these electrons by light years of empty space, measuring the spin of one will instantly determine the spin of the other. This seems to violate locality, the principle that influences cannot travel faster than light. The ER equals EPR conjecture offers a stunningly geometric resolution. It says that these two electrons are not actually separate in the way we think. The empty space between them is an illusion. In reality, they are connected by an ultra-tiny wormhole, a shortcut through the higher dimensional geometry of the universe. This wormhole is not a tunnel through ordinary space that you could ever travel through. It's unimaginably small, and it doesn't allow for faster-than-light communication. But it provides a physical structure for the entanglement. The particles are close together in the geometry of the bulk, even if they are far apart on the boundary. In this view, Einstein's spooky action at a distance isn't spooky at all. It's just geometry. The strange connectedness of quantum particles and the warped connectivity of wormholes are two different descriptions of the same underlying reality. When this idea was first proposed, it was understandably viewed as a highly speculative, if fascinating, metaphor. It was a beautiful story, but was it physics? How could one possibly prove that an abstract quantum correlation was equivalent to a tangible geometric tunnel? The conjecture has gained significant traction because it provides elegant solutions to some of the most vexing problems in theoretical physics, particularly the black hole information paradox. If you have two black holes that are entangled with each other, the ER equals EPR conjecture suggests they are connected by a giant wormhole. This provides a potential mechanism for information that falls into one black hole to exit through the other, preserving the sacred principle of information conservation without violating any laws of physics. It's a geometric picture that makes sense of how information can be both inside the black hole and simultaneously encoded on its horizon, as the holographic principle demands. The wormhole becomes the physical manifestation of the quantum entanglement between the black holes. The implications of this idea ripple out far beyond black holes, touching on the very nature of reality and connectivity. It suggests that the fabric of space itself might be woven from a vast cosmic web of quantum entanglement. Every time two particles become entangled, a new microscopic thread is spun into the tapestry of spacetime. In this view, empty space isn't really empty. It's a dense, dynamic network of these tiny wormhole connections linking everything to everything else. The reason we perceive a smooth, continuous, three-dimensional world is that we are seeing the average of an unfathomably complex quantum network from a great distance. Much like a piece of fabric looks smooth and continuous even though it is actually woven from countless individual threads. This concept provides a stunningly literal meaning to the idea of a connected universe. The bonds we form, the forces that hold matter together, and the very distance between stars might all be emergent properties of this underlying quantum geometric network. Susskind and Maldacner's work invites us to envision a cosmos where the deepest connections, whether between particles or people, are not merely philosophical concepts or fleeting emotions, but are literally etched into the fundamental architecture of spacetime, woven into the very geometry of existence. But if the universe is indeed a kind of cosmic computation, as so many of these breakthroughs suggest, then one philosopher's provocative thought experiment forces us to ask a truly ultimate question: who or what is running the program? In 2003, Swedish philosopher Nick Bostrom published a paper that would escape the halls of academia and ignite the imaginations of millions, formalizing an idea that had long been a staple of science fiction, but giving it a startlingly logical and probabilistic framework. He called it the simulation hypothesis, and its core argument is deceptively simple, built on a trilemma, a forced choice between three possibilities, only one of which can be true. Bostrom posits that at least one of the following statements must be true. First, that almost all civilizations at our level of technological development go extinct before becoming technologically mature. Or second, that almost all technologically mature civilizations lose interest in creating ancestor simulations, high-fidelity recreations of their past. Or third, we are almost certainly living in a computer simulation right now. The sheer power of this argument lies in its logical inevitability. If you believe that humanity is not on the verge of imminent self-destruction, and if you also believe that a future advanced civilization would possess both the immense computing power and the anthropological curiosity to run vast numbers of detailed simulations of its history, then the statistical odds tilt overwhelmingly in one direction. There would be one original base reality civilization, but potentially billions or even trillions of simulated realities running within it. If that were the case, the number of simulated minds would vastly outnumber the biological ones. Therefore, if you were a conscious being, the chances that you are living in one of those simulations, rather than in the original biological past, are astronomically high. We would not be the creators of the simulation, but rather, we would be the simulation conscious characters in an unfathomably complex video game created by our distant, post-human descendants. This idea resonates so powerfully because it dovetails eerily with several of the forgotten breakthroughs we've already explored. The holographic principle tells us that our three-dimensional reality might be a projection from a two-dimensional surface, much like a video game world is rendered from underlying code on a hard drive. Quantum mechanics, with its discrete, quantized properties and wave-function collapse upon observation, behaves suspiciously like a software program that only renders the fine details of reality when a user is looking at them, a common trick used in video game design to conserve processing power. Even the concept of a universe built from information rather than solid stuff fits perfectly with the simulation idea. If reality is fundamentally digital and computable, then what is it but a simulation running on a cosmic computer? Bostrom's hypothesis takes these abstract physical principles and gives them a startlingly personal and existential context. Unsurprisingly, the initial reaction from many scientists and philosophers was to dismiss the idea as unscientific metaphysics, an entertaining but ultimately untestable thought experiment no more valuable than speculating about an invisible dragon in your garage. How could one ever prove we are in a simulation? Any evidence we might find could itself be part of the simulation. However, the hypothesis has refused to fade away, gaining influential supporters who argue that it must be taken seriously. Astronomer Neil deGrasse Tyson has publicly given it better than 50-50 odds, while entrepreneur Elon Musk has famously stated that the odds we are not living in a simulation are 1 in billions. This has spurred a small but serious effort to find potential glitches in the matrix, testable signatures that might reveal the underlying computational nature of reality. Some physicists have proposed looking for evidence of a finite resolution to spacetime, much like the pixels on a screen, by studying the highest energy cosmic rays. Others suggest that any simulation would likely use shortcuts and approximations, especially in complex quantum calculations, and that these might leave subtle statistical footprints in experimental data that we could, in principle, detect. Beyond the physics, the simulation hypothesis forces us to confront profound philosophical questions about the nature of existence, consciousness, and free will. If we are simulated beings, are our thoughts and feelings any less real? If our actions are predetermined by the code of the simulation, do we truly have autonomy? Or is free will itself just an incredibly convincing algorithm running in our simulated brains? The hypothesis doesn't necessarily lead to nihilism. Instead, it could be seen as a modern, technological version of age-old philosophical questions about whether reality is fundamental or a kind of illusion, a theme that echoes from Plato's cave to Eastern philosophies of Maya. It challenges our anthropocentric view of the universe, suggesting that our entire cosmic history, from the Big Bang to the present day, might not be the foundational story, but merely a storyline, a narrative created for a purpose we cannot comprehend. Bostrom's breakthrough, though born in the field of philosophy, acts as a powerful mirror, reflecting our deepest anxieties and aspirations about technology, reality, and our place within it, urging us to question not just how the universe works, but what it ultimately is. For centuries, the concept of entropy was confined to the world of thermodynamics, a measure of disorder and randomness in systems like steam engines and glasses of ice water. It was the reason things fell apart, the arrow of time pointing inexorably toward a future of maximum blandness and chaos. A black hole, by stark contrast, was the ultimate symbol of simplicity and order. According to the pristine equations of general relativity, a black hole could be described by just 3 numbers: its mass, its electric charge, and its spin. It didn't matter if you threw a perfect diamond or a dumpster full of garbage into it. The black hole would digest it all and reveal nothing but these 3 bland parameters to the outside world. It was the ultimate cosmic eraser, and to suggest it had something as messy and complex as entropy seemed not just wrong but almost sacrilegious. This was the firmly held belief until a brilliant young graduate student named Jacob Bekenstein asked a question that seemed absurd: what happens to the information about all that stuff? Bekenstein, working under the guidance of the great John Wheeler, was grappling with a thought experiment that posed a deep problem. Imagine you have a box of hot gas, a system with a known high degree of entropy, and you push it across the event horizon of a black hole. From the perspective of the universe outside the black hole, that entropy has vanished, the gas is gone, and the black hole itself appears just a little bit more massive, but otherwise unchanged. This act seemed to allow for a decrease in the total entropy of the universe, a direct violation of the second law of thermodynamics, one of the most sacred principles in all of physics. The second law states that the total entropy of a closed system can never decrease. Bekenstein's radical proposal was that the second law could be saved if the black hole itself possessed entropy. He argued that when the box of gas disappeared behind the event horizon, the black hole's entropy must increase by at least the amount of entropy that was lost to the outside universe. But how do you calculate the entropy of an object that, by its very nature, was supposed to be featureless? His astonishing answer was that a black hole's entropy is not proportional to its volume, as one might intuitively guess for a three-dimensional object. Instead, it is proportional to the area of its event horizon. More precisely, he calculated that the entropy is equal to 1/4 of the horizon's area measured in Planck units, the smallest possible units of length. This was a result of breathtaking elegance and profound strangeness. It meant that the maximum amount of information a black hole could contain, because entropy is deeply linked to information, was not determined by how big it was on the inside, but by the size of its two-dimensional surface. Imagine a massive hard drive whose storage capacity isn't determined by its internal volume, but by the surface area of its outer case. Bekenstein's formula suggested that every bit of information about everything that ever fell into a black hole, every person, every planet, every shred of data, was not lost but was somehow encoded and smeared across its event horizon. The most famous and powerful critic of this idea was none other than Stephen Hawking. To Hawking, this was nonsense. A black hole with entropy must, by the laws of thermodynamics, also have a temperature. And an object with a temperature must radiate energy. But everyone knew that nothing, not even light, could escape a black hole's gravitational grip. The very definition of a black hole was that it was black, it could not radiate. Hawking set out to definitively disprove Bekenstein by showing that black holes could not possibly radiate. Instead, in a stunning twist of scientific fate, his calculations proved the exact opposite. By applying quantum theory to the space just outside the event horizon, Hawking discovered that black holes do, in fact, radiate. They emit a faint glow of particles, now known as Hawking radiation, and they do indeed have a temperature. This radiation causes them to slowly lose mass and eventually evaporate away entirely over astronomical timescales. Hawking had not only confirmed that Bekenstein was right about black holes having entropy and temperature, but he had also unlocked the mechanism of how they radiate. In a magnificent display of scientific integrity, Hawking publicly admitted his error and embraced Bekenstein's revolutionary insight, forever cementing the field of black hole thermodynamics. This partnership of ideas, born from initial conflict, gave us the Bekenstein-Hawking Formula, a cornerstone of modern theoretical physics. But it also created a new and even deeper puzzle, the black hole information paradox. If a black hole evaporates completely through Hawking radiation, and that radiation is purely thermal and random, carrying no information about what fell in, then the information about the original star, the spaceship, or the cup of coffee that crossed the horizon is irrevocably lost from the universe. This violates a fundamental tenet of quantum mechanics, which insists that information must always be preserved in principle, even if it's scrambled beyond recognition. The Bekenstein-Hawking formula had thrown down the gauntlet. forcing physicists to choose between the laws of quantum mechanics and the laws of general relativity. This paradox became the central driving force behind the next 50 years of research into quantum gravity. Bekenstein's work, initially seen as a heretical challenge to the purity of black holes, ultimately provided the first crucial clue toward resolving this very paradox. His insistence that information was stored on the horizon, not in the volume, was the seed that grew into the holographic principle. It suggested that our perception of a three-dimensional world might be a projection from a two-dimensional surface, with the event horizon acting as the ultimate cosmic hard drive. His formula forged an unbreakable link between information, gravity, and quantum theory, suggesting that these were not separate domains but different facets of a single, unified reality. In showing that even the most destructive and mysterious objects in the universe obey the laws of thermodynamics and information science, Bekenstein taught us that information is not just something we can know about the universe. It might be the most fundamental currency of the universe itself, the very stuff from which space, time, and matter are woven. In our world of digital abundance, we take the act of copying for granted. We duplicate files, clone hard drives, and make endless backups of our precious data. It's a fundamental power of the classical world, rooted in the idea that information is just a pattern of bits that can be read, written, and replicated perfectly. This ability to copy is so ingrained in our technology that we assume it's a universal right of information itself. But in the quantum realm, this assumption hits a wall, a fundamental, unbreakable law written into the fabric of reality itself. This is the no-cloning theorem, a deceptively simple but profound principle proven independently by physicists William Wouters, Wojciech, and Dennis Deeks in 1982. Their discovery revealed that in the quantum world, you cannot create a perfect, independent copy of an unknown quantum state. It is impossible. To understand why this is such a shocking departure from our everyday experience, consider the difference between a classical bit and a quantum bit or qubit. A classical bit is like a simple light switch. It's either definitively on or off, 1 or 0. You can look at it, see its state, and then build as many identical copies as you want. A qubit, however, is more like a magical, spinning coin that exists in a blur of both heads and tails simultaneously, a superposition. The moment you look at it to determine its state, this delicate superposition collapses into a single, definite outcome. The act of measuring it destroys the very quantum magic you are trying to copy. The no-cloning theorem states that there is no possible physical process, no matter how sophisticated, that can take an arbitrary, unknown quantum state and produce a perfect duplicate of it while leaving the original intact. Any attempt to measure the state to copy it will inevitably alter it. It's the ultimate copyright protection, enforced not by lawyers but by the fundamental laws of physics. Initially, this result was viewed as a fascinating but somewhat esoteric quirk of quantum theory, a curious limitation discussed in graduate seminars but with little practical consequence. It was another example of quantum weirdness, interesting but seemingly isolated from the larger world of applied physics. However, as the field of quantum information science began to blossom in the 1990s, the no-cloning theorem transformed from a theoretical curiosity into the very bedrock of an entire industry, quantum cryptography. Its impossibility became the source of ultimate security. Imagine two people traditionally named Alice and Bob want to communicate with absolute secrecy. Alice can send Bob a stream of photons, each prepared in a random quantum state. An eavesdropper, Eve, who tries to intercept and copy these photons to learn the secret key, will run headlong into the no-cloning theorem. She cannot copy the photons without measuring them, and her measurement will inevitably disturb their delicate quantum states. When Bob receives the photons, he and Alice can compare a small subset of their results over a public channel. If they find discrepancies caused by Eve's meddling, they know the line is compromised and they discard the key. If there are no errors, they know their communication is perfectly secure, guaranteed by the unbreakable laws of quantum mechanics. This is the principle behind quantum key distribution, and it offers a level of security that is provably impossible to achieve with any classical system. Beyond its practical application in cryptography, the no-cloning theorem forces us to confront a deeper philosophical truth about the nature of reality. In the classical world, information is abstract and detachable from its physical carrier. The same novel can be printed on paper, stored on a Kindle, or encoded in audio waves. The information is independent, but quantum information is different. It is inextricably tied to its physical instantiation. The state of a particle is the information. You cannot separate the two. This uniqueness and fragility are not bugs in the system. They are fundamental features that preserve the uncertainty and probabilistic heart of the quantum world. The theorem acts as a built-in protector of quantum weirdness, preventing us from using copying as a workaround to cheat the uncertainty principle and precisely measure complementary properties like position and momentum. It ensures that the quantum world remains fuzzy and indeterminate at its core. This profound limitation, far from being a hindrance, is actually what makes quantum computing so powerful. In a classical computer, copying bits is trivial. But this also means that information processing is linear and local. In a quantum computer, the inability to clone states is linked to the ability to perform massive parallel computations through superposition and entanglement. If you could clone quantum states, you could potentially use that power to solve problems like factoring large numbers through brute force, which would break the encryption that secures the internet. The no-cloning theorem prevents this, but it also enables the unique, non-linear logic of quantum algorithms that can solve certain problems exponentially faster than any classical machine ever could. It is a constraint that simultaneously defines the rules of the game and unlocks its most spectacular possibilities. The theorem teaches us that in the quantum realm, the inability to do one thing is often the very reason we can do another, more amazing thing. It shows us that the universe is not an open playground where anything is possible, but a carefully structured reality with its own inherent rules and protections, shaping what can and cannot be, and in doing so, defining the very nature of existence. Just as Bekenstein and Hawking revealed the shocking link between a black hole's information content and its surface area, a crucial question remained. Was this holographic property a strange quirk of black holes, or did it apply to the entire universe? Could any region of space, from a coffee cup to a galaxy cluster, have a fundamental limit on how much information it can contain? This question found its answer at the close of the 20th century, thanks to the brilliant work of physicist Raphael Bousso. In 1999, Bousso achieved a monumental feat. He derived a sweeping, universal law now known as the covariant entropy bound, a principle that generalized Bekenstein's discovery and placed a radical, all-encompassing ceiling on the information capacity of reality itself. Bekenstein's original bound was a landmark, but it had a limitation. It applied specifically to weakly gravitating systems that could be placed inside a static, spherical box. It wasn't immediately clear if this area scaling rule held true under all conditions, especially in the dynamic, expanding, and strongly gravitating context of the entire cosmos. Bousso's covariant bound cut through these restrictions with breathtaking elegance. his formulation was far more powerful and general. It states that if you take any arbitrary surface in space, the total information, or entropy, that can possibly pass through a certain type of light beam bundle emanating from that surface, what's called a light sheet, can never exceed 1/4 of the area of the original surface, measured in Planck units. While the mathematics is complex, the underlying message is stunningly simple. The maximum information content of any region of space is not determined by its volume, but by the area of its boundary. A giant sphere can't contain more information than can be encoded on its surface. The three-dimensional volume is an illusion. The two-dimensional boundary is what truly matters. To grasp the profound implications of this, let's use a simple analogy. Imagine a futuristic hard drive. In a classical, pre-Bousso world, you would assume that to double its storage capacity, you would need to double its volume, make it bigger on the inside. But the Bousso bound tells us that the universe doesn't work that way. Instead, to double the information capacity of a region of space, you only need to double the area of its surface. It's as if the true hard drive isn't the entire device, but just its outer shell. The interior volume is irrelevant for storage. It's the two-dimensional boundary that holds all the data. This transforms our view of the cosmos from a vast, three-dimensional container to something more like a giant, cosmic bubble, with all the information about everything inside it painted right onto its skin. This idea that the universe has a finite information capacity is a direct assault on our classical intuitions about space. We naturally imagine that space is continuous and infinitely divisible, that between any 2 points you can always find another point, and that you could therefore pack an infinite amount of information into even the tiniest volume. The Bousso bound shatters this notion. It suggests that reality is not continuous, but fundamentally discrete and pixelated at the tiniest possible scale, the Planck scale. There is a smallest possible unit of space and a fundamental limit to how much information can be stored there. The universe is not an analog system with infinite resolution. It is a digital system with a finite, albeit astronomically large, number of bits. The cosmos, in this view, is the ultimate but ultimately limited hard drive. When Bousso first published his work, it was highly technical, a dense piece of mathematical physics discussed and debated primarily by specialists in quantum gravity and cosmology. Its revolutionary nature was recognized, but its full implications took time to permeate the broader consciousness of physics. It was a rigorous proof that supported the still controversial holographic principle, providing it with a firm mathematical foundation that extended far beyond the specific case of black holes. Bousso had shown that the holographic principle wasn't just a metaphor. It was likely a fundamental law of nature, governing everything from the smallest particles to the largest scales of the universe. This bound challenges some of our most deeply held notions about infinity and reality. It implies that the universe, for all its apparent vastness, is finite in a very specific way. There is only so much information that can exist, so many possible events that can occur, so many distinct states that reality can assume. It places an ultimate limit on complexity. You could not, for example, have a galaxy with an infinite number of stars, each with an infinite number of atoms, because that would require infinite information, and the Bousso bound forbids it. The universe is not only finite in age and size, but finite in its informational essence. This realization forces us to confront the possibility that our reality, for all its richness and depth, might be a closed and complete system, a finite story with a finite number of pages, written on the inside of its own cover. Just when physicists thought they were closing in on a resolution to the black hole information paradox, a new and even more shocking problem erupted. threatening to tear apart the very foundations of physics. The year was 2012, and a team of 4 theorists, Ahmed Almary, Donald Marolf, Joseph Pulczynski, and James Sully, published a paper that would become instantly infamous. By carefully following the logical implications of the prevailing ideas, they arrived at a conclusion so violent and bizarre that it seemed to leave no room for compromise. Their argument was devastatingly simple. If quantum mechanics is correct and information is not lost in black holes, then an astronaut falling past the event horizon would not experience the serene, smooth spacetime predicted by Einstein's general relativity. Instead, they would be instantly vaporized by a searing wall of energy, a firewall, of unimaginably high energy particles blazing right at the point where the horizon should be. To understand how they reached this terrifying conclusion, we need to rewind to the core of the information paradox. Stephen Hawking had argued that information was lost forever when a black hole evaporates. But by the early 2000s, the majority of physicists, including Hawking himself, had come to accept that information must be preserved. The leading idea for how this happened was based on the concept of entanglement. Hawking radiation, the theory went, isn't completely random. The particles radiating away from the black hole are subtly entangled with particles that fell into the black hole long ago. This intricate web of quantum connections is how the information about the black hole's diet is slowly encoded into the outgoing radiation and returned to the universe. It's a delicate, precise quantum dance that ensures no information is ever truly lost. Almary and his colleagues, often referred to by the acronym AMPS, asked a very sharp question about this dance. They focused on 2 specific sets of entangled particles. The first set, call them A and B, are 2 particles of Hawking radiation emitted at different times. Because the radiation carries information, these 2 particles must be entangled with each other. The second entanglement is between a late-time Hawking particle, call it C, and its partner, particle D, which is just inside the event horizon. This is standard quantum behavior for particle pairs created from the vacuum. But here's the problem: a fundamental law of quantum mechanics, known as the monogamy of entanglement, states that a single quantum particle cannot be fully entangled with 2 different systems at the same time. It's the ultimate quantum love triangle. It's simply not allowed. For the information to be preserved, particle A and particle C must be entangled. But for the experience of an astronaut falling into the black hole to be smooth and uneventful, as Einstein's equations demand, particle C must be entangled with its partner, particle D, inside the horizon. The AMPS team showed that you cannot have both. It's an either-or choice. If you choose to save the information by preserving the entanglement between the Hawking particles, A and C, then you must sever the entanglement between particle C and its interior partner D. In quantum mechanics, severing an entanglement isn't a peaceful process. It releases a colossal amount of energy. The team calculated that this energy would manifest as an incredibly violent shockwave, a curtain of ultra-high energy particles right at the event horizon. The smooth vacuum of space would be replaced by a literal firewall that would incinerate anything attempting to cross it. This would resolve the information paradox by ensuring the entanglement required for information recovery, but it would do so at a catastrophic cost: the complete destruction of Einstein's principle of equivalence, which is the foundational concept that an observer in free fall should feel no special forces as they cross the horizon. The event horizon would no longer be a one-way ticket to an unknown fate. It would be an unambiguous death sentence, a blazing boundary in the sky. The physics community was thrown into an uproar. The firewall paradox was a direct assault on general relativity, the very theory that predicted black holes in the first place. It forced physicists into a trilemma, a choice between three deeply unpalatable options. 1. Information is lost and quantum mechanics is wrong. 2. Information is saved but Einstein is wrong and firewalls are real. Or 3. There is some deeper principle we are missing that resolves the contradiction. This third option has spawned a frenzy of creative and radical ideas. Some, like Leonard Susskind, have doubled down on black hole complementarity, arguing that the experience of the astronaut falling in and an observer watching from outside are both valid in their own reference frames and cannot be compared, a kind of cosmic agree to disagree clause built into reality. Others have proposed even more radical solutions, such as the idea that black holes don't have interiors at all, that what we perceive as a black hole is just a messy, hot membrane of information at the horizon, a concept called the fuzzball proposal. The most profound impact of the firewall paradox is not that it provided an answer, but that it so brilliantly exposed the raw, bleeding edge of our ignorance. It showed that our two most successful theories, the smooth, geometric universe of general relativity and the fuzzy, informational universe of quantum mechanics, are not just mildly incompatible. They are at war with each other under the most extreme conditions imaginable. The paradox suggests that our comfortable understanding of space and time as a continuous, reliable stage simply shatters at the event horizon of a black hole. The concepts of inside and outside may be classical illusions that break down, revealing a far stranger, more complex underlying reality where quantum entanglement and spacetime geometry are inextricably linked, perhaps even different manifestations of the same thing. This ongoing debate, now over a decade old, remains one of the most active and contentious in all of theoretical physics. It has not been resolved, but it has been incredibly productive. It has forced a complete re-evaluation of old assumptions and has become a powerful engine driving new research into quantum gravity, string theory, and the nature of information itself. The firewall paradox stands as a powerful testament to the scientific process. It demonstrates that progress is not always about finding comfortable answers, but about asking better and more devastating questions that expose the flaws in our current understanding, pushing us toward a deeper, more complete, and undoubtedly stranger vision of reality. For decades, the act of measurement in quantum mechanics has been portrayed as a violent, decisive event, a moment of truth that forces a fuzzy superposition to collapse into a single, definite outcome. It's the quantum version of asking a yes or no question and getting a firm answer. But what if we could ask a gentler question? What if, instead of demanding a particle to declare its position or spin with absolute certainty, we could simply ask for a hint, a whisper of what it might be doing, without startling it into choosing just one reality? This is the beautifully subtle idea behind weak measurement, a concept pioneered by Yakia Aharonov, David Albert, and Lev Vaidman in 1988. They proposed a way to peek at the quantum world without fully collapsing the wave function, and in doing so, they opened a window onto a bizarre landscape where particles can seemingly have properties that are not just unknown, but fundamentally indefinite, existing in a ghostly state of weak reality. The technique is as ingenious as it is counterintuitive. Imagine you want to measure the position of a single electron, but you don't want to shine a bright spotlight on it, which would force it to immediately pick a location. Instead, you use an incredibly dim light, a light so faint that each individual photon carries only the tiniest amount of information. This is the essence of a weak measurement. You weakly couple a measuring device to the quantum system you want to probe. Because the interaction is so gentle, the wave function doesn't collapse completely. The system is barely disturbed, and the measuring device, say a pointer on a dial, moves only a minuscule amount. On its own, this tiny deflection is practically meaningless, lost in the noise of the quantum world. It tells you almost nothing, but here's the magic. If you prepare an entire ensemble of identical quantum systems and repeat this gentle measurement on each one, the average of all those tiny, weak results can converge on a value that is shockingly well defined. This average is called the weak value, and these weak values are where things get truly strange. Because you're not forcing a collapse, the weak value can be a number that would be completely impossible for a single, strong measurement. In a strong measurement, a particle's spin might only ever be found to be +1 or -1, but its weak value could be 100 or -5 or even a complex number. The most famous example is a measurement that seems to suggest a photon can have a negative number of photons, a probability less than 0. This isn't an error, it's a direct consequence of the quantum math. These bizarre results aren't telling us what the particle's property is in a definite sense, but rather what its property is in relation to both its preparation and its eventual, final measurement, a concept Aharonov calls post-selection. It's as if the particle's entire history and its ultimate fate are both influencing this faint, ghostly trace of its existence in the present. When this idea was first introduced, it was met with deep skepticism and no small amount of confusion. To many physicists, it seemed like a mathematical trick, a clever but ultimately meaningless manipulation of statistics. If you can't get a result like 100 from a single measurement, they argued, then it can't be real. It was dismissed by some as an artifact of the averaging process, not a genuine property of the quantum system itself. The concept of weak reality, the idea that a property could be real in this fragile, contextual way, challenged the very definition of what it means for something to be real in physics. It suggested that reality might not be a binary switch, flicking between is and isn't, but a dial with a continuous spectrum, including strange and seemingly impossible settings. The tide began to turn as experimental technology advanced. Starting in the early 2000s, physicists began designing exquisitely precise experiments to test these predictions. They used weak measurements to probe the trajectories of photons in the famous double-slit experiment. According to standard quantum mechanics, a photon doesn't have a well-defined path, it goes through both slits. But by performing weak measurements on millions of photons, and then post-selecting only those that landed at a specific point on the detector, researchers were able to reconstruct an average path. Astonishingly, these average paths showed the photon behaving in a way that looked almost like a weird particle, but one that could, on average, sometimes seem to loop back and forth in ways a classical particle never could. These weak trajectories provided a stunning visual representation of a quantum system's behavior that was neither a definite particle path nor a simple wave, but something in between, a ghostly echo of all possible paths. This forgotten breakthrough has given us an entirely new lens through which to examine quantum paradoxes. It has been used to provide intuitive pictures for how quantum particles can seem to be in two places at once and to shed light on the nature of quantum tunneling. But its greatest contribution might be philosophical. Weak measurement blurs the hard line we've drawn between the possible and the actual. It suggests that before a strong measurement forces a definitive outcome, quantum properties exist in a state of potential reality, not just unknown, but physically manifest as a tendency or a propensity that can be gently probed. This challenges the Copenhagen interpretation's stark division between the quantum world and the classical world of measurement. It implies that measurement isn't a magical act that creates reality from nothingness, but rather a process that amplifies one specific potentiality from a rich soup of faint, coexisting possibilities. Aharonov's work invites us to see the quantum world not as a realm of sharp edges and sudden collapses, but as a continuous, nuanced spectrum of existence, where what is real depends profoundly on how gently we choose to look. Now, if the firewall paradox shows us how our theories can clash at the edge of a black hole, there is another problem, far more vast in scale, that highlights a contradiction sitting right at the heart of our understanding of the entire cosmos. This isn't a conflict at a horizon, it is a discrepancy woven into the very fabric of empty space itself. It is known as the cosmological constant problem, and it is not just a puzzle, it is the single greatest embarrassment in all of modern physics, a numerical catastrophe so severe that it represents a complete breakdown of our ability to describe reality. To understand this problem, we must return to the strange quantum energy of the vacuum that we encountered with the Casimir effect. Quantum field theory tells us that empty space is not truly empty, but is instead a seething, bubbling foam of virtual particles constantly flickering in and out of existence. Every single point in the vacuum is teeming with this activity, and all of it contributes to a background energy density. This isn't just a theoretical idea, we can actually calculate this energy. Physicists add up the contributions from every known quantum field, the electromagnetic field, the electron field, the quark fields, all of them. And when they do the math, they arrive at a number for the energy density of the vacuum. This number is astronomically, unimaginably large, but here's where the problem begins. In Einstein's theory of general relativity, energy, including the energy of empty space, has a gravitational effect. This vacuum energy should act as a kind of anti-gravity, causing the very fabric of spacetime to push itself apart. This repulsive force is what cosmologists call the cosmological constant. So, if our quantum calculation of the vacuum energy is correct, this immense energy should be causing the universe to expand at a truly violent, explosive rate. Galaxies should be torn apart from each other so rapidly that it would be impossible for any stars, planets, or life to ever form. The cosmos would be a thin, cold, and utterly lifeless soup of particles flying apart in a fraction of a second. Yet, when we look out at the actual universe with our most powerful telescopes, we see something completely different. We do observe that the expansion of the universe is accelerating, a discovery that won the Nobel Prize in 2011. This acceleration is driven by something we call dark energy, which behaves exactly like a cosmological constant, but the measured value of this constant is incredibly, delicately small. It is there, but it is 120 orders of magnitude smaller than the value predicted by quantum field theory. To grasp how colossal this error is, imagine predicting that the distance from the Earth to the Sun is about 150 million kilometers, but then going outside with a ruler and measuring that same distance to be smaller than the width of a single atom. The discrepancy is that vast, that utter, and that humiliating. It is by far the worst theoretical prediction in the entire history of science. This chasm between prediction and observation is the cosmological constant problem. It tells us in no uncertain terms that something is profoundly wrong. Either our understanding of the quantum vacuum is completely mistaken, or our theory of gravity breaks down in this context, or most likely both. For decades, this problem has been the elephant in the room of fundamental physics. It is so intractable that many researchers simply set it aside, focusing on problems that seem more solvable with our current tools. It's a kind of accepted embarrassment, a known unknown that we quietly acknowledge before moving on to other topics. But for those who do grapple with it, the proposed solutions are as radical as the problem is deep. One leading idea is supersymmetry, an elegant theory that proposes every known particle has a hidden super-partner particle. If supersymmetry were unbroken, the positive and negative contributions of these partner particles to the vacuum energy would cancel each other out perfectly, leaving a net of zero. The problem is, we see no evidence of these superpartners at the energy scales we've probed, meaning supersymmetry, if it exists, must be a broken symmetry. The cancellation would then be very good, but not perfect, potentially leaving behind the tiny residual energy we observe as dark energy. However, the ongoing failure to detect any supersymmetric particles at the Large Hadron Collider has made this solution less compelling to many. Another, more philosophical approach is the anthropic principle. This line of reasoning suggests that the cosmological constant isn't determined by a fundamental law, but is instead a random variable that can take on different values in different parts of a vast multiverse. In the overwhelming majority of these universes, the constant is far too large, and those universes expand too fast for galaxies or life to form. We, of course, find ourselves in one of the incredibly rare universes where the constant is minuscule, simply because our existence requires it. This is not so much an explanation as an acknowledgement that some things might just be environmental accidents, not derivable from first principles. Beyond these, the problem screams for entirely new physics, a revolutionary idea that we haven't yet conceived. Perhaps the vacuum energy is somehow locked away in extra dimensions, inaccessible to our gravitational field. Perhaps gravity operates differently on the largest scales, a modification of Einstein's equations that would naturally cancel out this huge energy. Or perhaps the answer lies in the nature of time itself, or in a deeper connection between quantum information and spacetime geometry, as suggested by the holographic principle. Ultimately, the cosmological constant problem is more than just a numerical puzzle. It is a profound reminder of our ignorance. It forces us to confront the possibility that our two most successful theories, quantum mechanics and general relativity, are not just incompatible, they might be fundamentally incapable of being united without a paradigm shift so great that it will rewrite our conception of reality. Resolving this problem could reveal whether our universe is delicately fine-tuned by chance, or if there is a beautiful, deeper principle governing the vacuum that we have yet to discover. It stands as a monument to the fact that the universe still holds mysteries vast enough to humble our greatest intellects. Stephen Hawking's brilliant revelation that black holes radiate energy was a monumental leap forward, but it came with a terrifying catch: the information paradox. If a black hole evaporates completely into a featureless bath of thermal radiation, then the quantum information about everything it ever consumed is seemingly erased from the universe, violating a fundamental tenet of quantum mechanics. For decades, physicists have wrestled with this apparent contradiction, searching for any possible escape route. One particularly elegant and overlooked solution emerged in the 1980s, proposing that black holes might not only radiate photons, but also a far more elusive and ghostly particle, the neutrino. This idea suggests that these tiny, near-massless messengers could be the key to preserving the cosmos's memory, carrying secrets out from behind the veil of the event horizon in a way that Hawking radiation alone cannot. Neutrinos are nature's most elusive ghosts. Trillions of them pass through your body every second, coming from the sun, from distant supernova, and from the Earth's own radioactive decay, yet they rarely interact with anything. They have no electric charge and almost no mass, allowing them to travel through light years of lead without a single collision. This very property that makes them so difficult to detect also makes them the perfect candidate for a cosmic escape artist. The theory of black hole neutrino radiation proposes that the intense gravitational and quantum forces at play near the event horizon could catalyze the creation and emission of neutrinos and potentially other exotic particles. Unlike Hawking radiation, which is predominantly photons and arises from quantum fluctuations in the vacuum, this neutrino flux could be directly tied to the quantum states of the matter that originally formed the black hole. In essence, these neutrinos wouldn't just be random thermal noise. They could be subtle messengers encoded with faint, fragile traces of the information that fell in. They would be a faint whisper amidst the roar of Hawking's thermal shout, a whisper telling the story of the black hole's past. When this idea was first proposed, it was almost immediately sidelined, dismissed as a theoretical curiosity with no hope of ever being tested. The signals would be unimaginably faint, a whisper lost in a hurricane. Detecting the already subtle Hawking radiation from anything but the smallest, hottest black holes is considered a technological fantasy far beyond our current capabilities. Trying to pick out an even fainter neutrino signal from a specific black hole against the overwhelming background noise of the universe's constant neutrino barrage seemed like pure science fiction. Furthermore, the complex physics of how exactly these neutrinos would be generated and encoded with information was, and still is, poorly understood. The idea was shelved, another interesting but impractical footnote in the long struggle to understand quantum gravity. Yet, as is so often the case in science, time and technology have a way of resurrecting forgotten ideas. We are now living in the dawn of a new era of multi-messenger astronomy, where we don't just observe the universe with light, but with gravitational waves and, crucially, with neutrinos. Incredible facilities like the Ice Cube Neutrino Observatory, a gigantic telescope buried deep in the Antarctic ice, are now routinely detecting high-energy neutrinos from the most cataclysmic events in the cosmos, like colliding neutron stars and active galactic nuclei. While we are still far from having the sensitivity to detect the hypothetical neutrino glow from a typical stellar mass black hole, the mere fact that we can now point to a region of the sky and say, "A neutrino came from there," is a revolutionary step forward. The next generation of neutrino detectors, planned to be even more massive and more sensitive, could one day be tuned to listen for the specific, predicted signatures of black hole neutrino radiation. What was once a purely theoretical Hail Mary pass is now, however distantly, within the realm of future experimental possibility. The profound implication of this breakthrough is that black holes would not be the ultimate prisons we once imagined. If neutrinos or other particles are indeed carrying information away, then black holes are not truly black, and they are not true information destroyers. They would be subtle information processors, transforming and translating the complex quantum states of infalling matter into an incredibly faint, incredibly stable neutrino code that is broadcast back into the universe. This would provide a beautiful and natural resolution to the information paradox, preserving the unitarity of quantum mechanics without requiring any violent revision of physics like the firewall. It suggests a deep and elegant unity between the world of the very small, the quantum realm of particles and information, and the world of the very large, the gravitational realm of black holes and spacetime. The universe, in this view, finds a way to preserve its history not through dramatic means, but through the faintest, most persistent signals imaginable, ensuring that every bit of information, from a supernova to a single atom, is never truly lost, only transformed and patiently waiting for us to learn how to listen. But if the universe is a cosmic computation, as the holographic principle and quantum information theory suggest, then we are forced to ask a truly foundational question: what is the hardware? Our journey through these forgotten breakthroughs has progressively dismantled our assumptions, showing that particles, forces, and even spacetime might not be fundamental. We've peeled back layer after layer, but what lies at the very bottom? This search for the ultimate substrate of reality brings us to one of the most ambitious and speculative ideas of all: a concept championed by the great John Wheeler himself in the 1960s. He called it progeometry, the radical proposal that space and time themselves are not the starting point of physics, but are instead secondary, emergent properties that arise from something even more basic, a something that exists before geometry itself. Wheeler, who had already revolutionized physics with his work on nuclear fission and quantum theory, was deeply captivated by the deepest questions of existence. He understood that the relentless paradoxes of quantum gravity, the singularities in black holes, the problem of measurement, were not just puzzles to be solved within the current framework. They were screaming signs that the framework itself was wrong. He began to envision a reality where the smooth, continuous stage of spacetime, which Einstein had described as a dynamic fabric, was actually an illusion. This illusion, he proposed, emerges from a vast, chaotic, and fundamentally non-geometric underlying reality. He famously described this substrate as a kind of quantum foam, a seething, turbulent sea of unimaginably small fluctuations occurring at the Planck scale, where the very concepts of here and now break down into a fuzzy, probabilistic chaos. In this foam, wormholes and tiny tunnels would constantly blink in and out of existence, creating a dynamic, ever-changing topology. Wheeler's progeometry was the ultimate reductionist dream, to find the cosmic atoms from which the architecture of spacetime itself is built. For decades, this vision remained precisely that, a visionary's dream, a compelling but highly speculative metaphor that was incredibly difficult to translate into rigorous mathematics. How do you build a theory of something that exists before space and time, using a language of mathematics that is itself deeply rooted in those very concepts? It was a philosophical guiding star without a precise map. Yet, the power of Wheeler's intuition was so profound that it refused to die. It became the inspirational seed for several of the most active and promising approaches to quantum gravity that we have today. Loop quantum gravity, for instance, takes the idea of discreteness to heart. It proposes that space is not smooth and continuous, but is instead woven from tiny, finite loops, one-dimensional threads of gravitational field. The fabric of space is actually a network of these loops, a spin network, and what we perceive as a smooth, three-dimensional volume is actually built from the vast number of these discrete, quantized units, much like a digital photograph appears smooth and continuous despite being made of individual pixels. Similarly, the theory of causal sets offers another breathtakingly simple yet powerful realization of Wheeler's progeometric vision. In this approach, the fundamental ingredients of reality are not particles or fields, but simple, abstract events. The entire universe is just a vast collection of these events, with only one single primitive relation between them, a basic before and after, ordering that denotes which event can influence another. This is the causal in causal sets. There is no space, no distance, no duration in this fundamental description, only a vast, partially ordered set of events with causal relationships. Astonishingly, from this sparse, minimalist structure, the familiar four-dimensional spacetime of our experience is predicted to emerge. The smooth continuum of space and the flow of time are approximations that arise from the sheer density and complexity of this underlying network of causal relations. The distance between 2 points and the time between 2 events are not fundamental. They are statistical, large-scale properties that crystallize from the collective behavior of countless elementary events, much like the temperature of a gas emerges from the frantic motion of its molecules. The profound implication of progeometry is that the void we call empty space is not passive and static. It is a dynamic, frenetic, and deeply structured nothingness. At the Planck scale of 10 to the negative 35 meters, the universe is not a calm, empty stage. It is a boiling ocean of potentiality, a foam of virtual events constantly reconfiguring the very meaning of here and now. This challenges our most basic sensory experience. We move through a world that feels smooth, continuous, and voluminous. We experience time as a flowing river. Progiometry tells us that this is a compelling illusion, a user interface generated by our macroscopic scale. The true reality beneath is granular, discrete, and relational. There is no such thing as absolute location or absolute time. There are only relationships between events. This idea echoes the philosophical concept of relationalism, championed by Leibniz centuries ago, who argued that space and time are not containers but are merely the set of all relations between objects and events. Wheeler's progiometry provides a potential physical mechanism for this philosophy, suggesting that the universe is fundamentally a vast web of connections, and what we call spacetime is the shape that web takes when viewed from within. Wheeler's forgotten breakthrough, though initially a dream, continues to inspire because it addresses the most profound limitation of our current physics. We are trying to describe the genesis of the stage using the language of the actors who perform upon it. To truly understand quantum gravity, we may need to discover a new language, one that describes a reality without space and without time, a progiometric world of pure information, relation, and logic. His vision invites us to consider that the ultimate nature of reality might not be geometric at all, but something far more abstract and strange, a cosmic code waiting to be deciphered, whose output is the breathtakingly realistic simulation of a spacetime universe that we call home. The firewall paradox had plunged physics into a state of crisis, forcing an impossible choice between the sanctity of quantum information and the smooth spacetime of general relativity. It seemed there was no escape from this logical trap, no way to satisfy both of our most successful theories without one of them being brutally violated at the event horizon. But from this intellectual impasse, a radically different and deeply philosophical solution emerged, one that asked not which law of physics was wrong, but whether our very notion of a single, objective reality was the problem. In 1993, Leonard Susskind and his colleagues introduced a concept of breathtaking audacity, black hole complementarity. This principle proposed that the fiery death of the firewall and the serene passage of the astronaut were not mutually exclusive truths. They could both be completely and simultaneously true, but for different observers. There is no single, God's eye view of reality. Instead, the universe provides two perfectly valid but utterly incompatible descriptions of what happens at a black hole, and the key to resolving the paradox is to never, ever mix these two perspectives. This idea is a direct and powerful extension of the quantum complementarity that Niels Bohr championed decades earlier. In the classic double-slit experiment, an electron can behave as either a particle or a wave. Which description is correct depends entirely on how you choose to measure it. You can't see both natures at the same time with a single apparatus. The experimental setup you choose determines the reality you will observe. Black hole complementarity applies this same logic to the most extreme gravitational environment imaginable. It asserts that the experience of an observer who stays safely outside a black hole and the experience of an astronaut who foolishly jumps in are both 100% valid within their own frames of reference, but they are fundamentally complementary. They cannot be combined into one coherent picture because that would require comparing notes across the event horizon, which is strictly forbidden by the laws of physics. From the outside observer's perspective, all information about the infalling astronaut is smeared across the event horizon, scrambled and eventually radiated back out as Hawking radiation. This observer would indeed see anything crossing the horizon get vaporized into a thermalized mess. But from the astronaut's perspective, as they cross the horizon, nothing special happens at all. The local laws of physics hold perfectly, spacetime is smooth, and they continue on their journey toward the central singularity, completely oblivious to the fiery fate the outside universe has assigned to them. The most controversial aspect of this idea is that it appears to blatantly violate a cornerstone of general relativity, the equivalence principle. This principle, which is the very foundation of Einstein's theory, states that an observer in free fall should not feel any special forces. They should be unable to tell by any local experiment that they have crossed the point of no return. Black hole complementarity protects this principle for the falling astronaut. However, it does so at the cost of another cherished concept, the objective reality of information. The same quantum bit of information seems to be in two places at once. From the outside, it's encoded on the horizon. From the inside, it's carried by the astronaut. This seems to violate the quantum no-cloning theorem. Suskind's brilliant resolution was to show that this is not a true violation because no single observer can ever witness both copies. The outside observer sees the information on the horizon but cannot see it inside, and the infalling observer sees it inside but has no way to communicate that fact back across the horizon to the outside world. The paradox only arises if you illegitimately try to stitch these two perspectives together into a single, overarching narrative. The universe, in its deepest workings, does not allow for that kind of universal narrative. Reality is not a single story but a collection of stories, each complete and consistent for its narrator. This radical perspectivalism is perhaps the most profound and humbling implication of black hole complementarity. It suggests that the search for a single, objective description of the universe, a complete theory of everything in the classic sense, might be a philosophical mirage. The truth about reality might be inherently multifaceted, a complex diamond that reveals a different facet depending on the angle from which it is viewed. This doesn't mean that anything goes or that reality is subjective. The laws of physics are rigid and absolute within each frame, but it does mean that our human desire for one simple, absolute story may be fundamentally at odds with the architecture of the cosmos. This breakthrough forces us to embrace a more nuanced and sophisticated view of truth, one where we must hold multiple, contradictory descriptions in our minds at once, and understand that they are all equally real, yet forever separated by causal boundaries. In the decades since its proposal, black hole complementarity has grown from a controversial speculation into a cornerstone of modern quantum gravity research. It provides a powerful framework for thinking about the information paradox without resorting to the violent and paradigm-shattering introduction of firewalls. It demonstrates how the principles of quantum mechanics, born from the study of the impossibly small, might extend their jurisdiction seamlessly into the realm of the impossibly dense, governing the fate of black holes and the information they contain. This duality, this ability of the universe to present two faces for one event, is not a bug but a feature, a deep and elegant mechanism for preserving the consistency of physical law across all domains of experience. It shows us that the path to unifying physics may not lie in forcing one theory to submit to another, but in learning to speak a language that can gracefully accommodate the beautiful and necessary contradictions of a reality that is far richer than any single viewpoint could ever capture. While we often imagine the universe as a collection of particles pushing and pulling on each other through forces across the stage of space, what if the most fundamental truths aren't about the actors or the forces, but about the very shape of the stage itself? This is the radical shift in perspective offered by a branch of mathematics so abstract it was once considered pure intellectual play, with no conceivable connection to the real world. In 1988, the renowned mathematician Michael Atiyah, along with other pioneers, formalized a framework called Topological Quantum Field Theory, or TQFT. This was not a theory of physics in the traditional sense, but a new way of thinking about what physics could be. It proposed that the most important aspects of a physical system might not depend on the local, nitty-gritty details, the exact distances between points or the specific forces at play. Instead, they might depend solely on the global, overall shape of the space the system inhabits. It's the difference between describing a donut by meticulously measuring the curvature of every millimeter of its glaze and simply counting that it has one hole. That number of holes is a topological invariant, a property that doesn't change if you stretch, twist, or bend the donut, as long as you don't tear it or glue new parts to it. Atiyah's work suggested that the universe might be filled with similar, profound invariants that remain constant no matter how much the local details jiggle and change. One of the most spectacular realizations of this idea is a specific TQFT known as Chern-Simons theory. This theory describes a world where particles are not the fundamental objects we once thought. Instead, they emerge as excitations or knots in a field that is deeply connected to the topology of space. The behavior of these particles is bizarre and wonderful. They can have fractional statistics, meaning they are neither purely bosons nor fermions. Some, known as enyons, remember the history of how they've been moved around each other. If you take one enyon and loop it around another, the quantum state of the system isn't just changed. It's transformed in a way that depends on the specific braiding path taken, as if the universe is keeping track of the dance. This isn't just abstract math, it's a prediction about how matter could behave in a universe where topology is king. For years, this remained a beautiful piece of mathematics, a playground for theorists that seemed too exotic to ever find a home in our messy, real-world physics. How could something so pristine and global possibly survive the violent, local chaos of actual materials? The answer came from an unexpected frontier: condensed matter physics. Researchers began to discover that inside certain extraordinary materials, electrons collectively organize themselves into states where their behavior is exactly described by these topological field theories. The most famous examples are topological insulators. These are materials that are insulators on the inside but perfectly conducting on their surface. You can scratch the surface, introduce impurities, or deform the material, and those surface electrons will keep flowing without resistance. Their conductivity is protected not by the material's purity, but by its global topological property, that invariant number like the donut's hole. It's a robustness that engineers can only dream of, a form of stability written into the very shape of the electron's universe within the material. This robustness is the true gift of topological physics, and it's the reason this forgotten breakthrough is now at the forefront of the most advanced technological pursuit on Earth: quantum computing. The greatest enemy of a quantum computer is decoherence, the tendency for the fragile quantum states of its qubits to be disrupted by the slightest noise or imperfection in their environment. It's like trying to balance a pencil on its point in a hurricane. But what if you could build a qubit whose state was defined not by the precarious energy level of an atom, but by a topological property? A property that is immune to local jostling because it depends on the global arrangement of the system. This is the promise of topological quantum computation. The quantum information would be encoded in the braiding of enyon world lines. Think of it as storing data not in a 0 or a 1, but in the specific knotting and twisting of particle paths. To change the information, you would have to perform a major global operation like untying a complex knot. A tiny local perturbation, a vibration, a stray electric field would be powerless to affect it. It would be like trying to change the number of holes in a donut by poking it with a finger. The local poke does nothing to the global structure. This isn't just incremental progress, it's a potential revolution in stability, offering a path to fault-tolerant quantum systems that could finally fulfill the world-changing promise of the technology. The profound implication of topological quantum field theory is that it invites us to see the cosmos through a completely different lens. For centuries, physics has been focused on local forces and particles, the actors, and their interactions on the stage. TQFT suggests that the most fundamental script might be about the stage itself, its shape, its connectivity, its holes and handles. It proposes that what is most real and most durable in the universe are not the things that change, but the things that cannot be changed by any local disturbance. This is a move from reductionism to holism, from analyzing the smallest parts to understanding the whole. It forges a deep and unexpected connection between the abstract world of pure mathematics, specifically geometry and topology, and the concrete world of physical phenomena. We are encouraged to think less in terms of billiard balls and forces, and more in terms of knots, braids, and invariants. This breakthrough from the late 1980s, once a towering peak of abstraction, has now descended into the valleys of experiment and application, offering not just new calculations, but a whole new way of imagining the bedrock of reality itself. For centuries, our description of the universe has relied on a silent, unchanging stage, a background of absolute space and absolute time. This was the framework Newton gave us, and even Einstein, who wove them together into spacetime, still treated this fabric as the ultimate arena against which all events play out. It's a perspective we take for granted, a view from nowhere that allows us to impartially observe and measure the world. But what if this godlike perspective is an illusion? What if there is no neutral stage, no privileged vantage point from which to describe reality? This is the profound challenge posed by the concept of quantum reference frames, an idea championed by physicists like Carlo Rovelli that suggests every property in the universe is only meaningful in relation to something else. There is no here without a there, no now without a then, and no definite property of any particle without another particle to relate to. This relational approach, known as relational quantum mechanics, directly tackles some of the most baffling aspects of the quantum world, particularly the infamous measurement problem. In the standard view, a particle exists in a blurry superposition of states until it is measured by a large classical instrument, which mysteriously causes the wave function to collapse into a single outcome. But this raises an endless chain of questions. What counts as a measurement? When does it happen? And who measures the measurer? Rovelli's relational framework cuts through this knot with a beautifully simple yet radical proposition. There is no such thing as an absolute state of a system. Properties like position, momentum, or spin are not inherent to an object. They only exist as relationships between physical systems. An electron does not have a definite spin on its own. It only has a spin relative to another system, say, a measuring apparatus, and that apparatus, in turn, only has a definite pointer reading relative to yet another system, like a scientist's eye or a computer monitor. There is no collapse, only the revelation of a property within a specific relational context. What looks like a definite measurement from your perspective might still be a fuzzy superposition from the perspective of a different, faraway observer. This isn't a paradox, it's just the nature of a reality where every fact is a shared fact between interacting entities. When this idea was first developed in the late 1990s and early 2000s, it was largely sidelined. It was seen by many as a philosophical reinterpretation of quantum mechanics rather than a practical advance. It was so counterintuitive, so challenging to our deepest assumptions about an objective world out there, that it was easier to set it aside and continue wrestling with the measurement problem within the more familiar, absolute framework. The notion that reality is co-created through interactions seemed to venture too far into the realm of subjectivity, making many physicists deeply uncomfortable. How could you build a solid, predictive science on a foundation of relations without any fundamental things to relate? Yet, in recent years, this forgotten perspective has stormed back into the forefront of fundamental physics, precisely because it offers a promising path to the ultimate goal, uniting quantum theory with general relativity. Einstein's theory of gravity is at its heart already a profoundly relational theory. It tells us that there is no fixed spacetime background. The geometry of the universe is dynamic and is shaped by the matter and energy within it. You cannot talk about location or motion without specifying it relative to other objects. Quantum reference frames provide the missing language to extend this relational philosophy into the quantum domain. Researchers are now exploring how to describe quantum physics from the perspective of a particle itself, treating it not as an object in a background field, but as the very anchor for its own reality. In this view, what we call a quantum field might not be a thing that exists in spacetime, but rather a set of relationships from which spacetime itself emerges. The universe begins to look less like a collection of objects and more like a vast, evolving network of connections, a cosmic web where each node defines its reality only through its links to all the others. The most breathtaking implication of quantum reference frames is the complete dissolution of the view from nowhere. There is no external observer, no impartial God's eye perspective. Every description of reality is from a point of view within the universe itself. We are not outside the system looking in. We are nodes in the network, interacting with other nodes and co-creating the reality we measure through those interactions. This suggests that existence is fundamentally dialogical, a constant conversation between physical systems. The solidity of the world we experience is not an illusion, but it is a shared truth, a consensus reality stabilized by countless trillions of these relational interactions. This forgotten breakthrough does more than just solve a technical problem in quantum mechanics. It offers a radical new ontology. It tells us that the universe is not a pre-written script performed on a fixed stage, but an improvisational dance where the dancers and the dance floor bring each other into being through every step they take. And now we arrive at a concept so profound it might just be the master key that unlocks the final door. The idea that space and time themselves are not the foundation of reality, but are instead a magnificent illusion woven from the most fundamental connection in the universe, quantum entanglement. If the holographic principle suggests our reality is a projection from a two-dimensional surface, this next breakthrough asks a far more radical question. What is the projector, and what is the light source that creates the stunningly realistic three-dimensional image we call the cosmos? The startling answer proposed by physicists like Mark van Romsdonk is that the projector is nothing other than the strange, spooky links between particles, and the light is the sheer intensity of their quantum intimacy. In this view, the empty space between stars and the distance between your hands are not fundamental truths. They are a story told by entanglement, a narrative of connection that makes Chinese letter feel like distance. To grasp this, let's start with a simple, powerful analogy. Imagine the universe as an immense cosmic tapestry. From a distance, it looks like a smooth, continuous picture with depth, texture, and clearly defined objects separated by empty space. But if you were to bring a magnifying glass right up to the fabric, that illusion would shatter. You would see that the image is not painted on a solid canvas at all. Instead, it is woven from countless individual threads. The depth, the shadows, the appearance of separation between figures, all of it emerges from the specific way these threads are looped, tied, and connected to one another. The threads themselves have no volume or depth. They are one-dimensional. The breathtaking three-dimensional scene exists only because of the pattern of their connections. Now, in this analogy, the individual threads are the fundamental quantum particles or fields, but the knots, the loops, the ties that bind them together, those are quantum entanglement. The fabric of spacetime isn't the canvas, it is the intricate, interconnected weaving itself. Van Romsdonck's crucial insight was to take this beautiful metaphor and give it mathematical teeth using the tools of the AD/CFT correspondence. He explored what would happen to the spacetime in the holographic bulk if he began to carefully sever the quantum entanglements on the boundary. The result was as dramatic as it was illuminating. As he reduced the entanglement between different regions of the boundary theory, the geometric connection between the corresponding regions in the bulk spacetime began to weaken and pull apart. It was as if the very glue holding space together was dissolving. If he completely removed the entanglement between 2 points, the spacetime between them would not just stretch, it would undergo a geometric phase transition and literally tear apart, forming a deep chasm, a phenomenon that looks exactly like a wormhole. This mathematical exercise suggested a direct and stunning correspondence. More quantum entanglement on the boundary equals a tighter, smoother, more connected geometry in the bulk. Less entanglement equals a frayed, disconnected, and torn spacetime. The conclusion was inescapable. Einstein's smooth, geometric spacetime doesn't just correlate with quantum entanglement, it is built from it. Entanglement isn't just a feature of the universe, it is the cosmic loom on which the universe is woven. This idea transforms our understanding of the most basic experience of separation. Why are two objects that are far apart difficult to bring together? Classical physics says because you have to move through all the intervening space. But the emergent spacetime view offers a deeper answer, because there is simply less quantum entanglement between them. The distance is not a primary physical barrier, it is a manifestation of a lack of connection at the fundamental quantum level. Conversely, two particles that are intensely entangled, even if they are light years apart according to our map of space, are, in the truest physical sense, close together. Their geometric separation is an illusion, their quantum intimacy is the reality. This turns the EPR paradox on its head. Einstein's spooky action at a distance isn't an action across space, it is the revelation that the particles were never truly separate to begin with. The space between them was the illusion. For a long time, this was a compelling but abstract argument confined to the pages of theoretical physics journals. How could one ever test such a thing? The breakthrough is that we now can, or at least we are designing experiments that could provide strong circumstantial evidence. One proposal involves using large arrays of quantum computers. By carefully controlling the degree of entanglement between their quantum bits, or qubits, researchers could look for signatures that their system is beginning to exhibit emergent geometric properties. It would be like watching the tapestry form from the threads right before your eyes. Another approach involves analyzing the cosmic microwave background for subtle statistical patterns that could only be explained by an underlying quantum informational structure to spacetime. These are incredibly difficult experiments, but the mere fact that they are being seriously proposed shows how this once metaphorical idea is hardening into a testable scientific framework. The implication of this is perhaps the most profound of all our 30 breakthroughs. It suggests that the ultimate nature of reality is not material but relational. The universe is not a collection of things that are connected. It is a collection of connections that manifest as things. What we perceive as solid, separate objects sitting in a vast container of space are actually dense knots of relationship in a vast network of quantum information. Space is not the stage for the drama of physics. It is a main character in that drama, and its lines are written entirely in the language of entanglement. This invites us to see the cosmos not as a cold, empty void dotted with lonely islands of matter, but as a vibrant, living web of intimacy, where every particle, every star, and every conscious being is fundamentally and inseparably linked to the whole. The distance between us is a story, but the connection is the truth. But if the universe is a vast network of entanglement, a cosmic web of relations from which space and time themselves emerge, then we are forced to confront a final, staggering question that has haunted philosophy and science for millennia. What is the nature of the thing that is experiencing all of this? What is consciousness, and what role does it play in this grand architecture of reality? It is here, at this ultimate frontier, that we encounter perhaps the most radical and mind-bending proposal of all, one that doesn't just place consciousness in the driver's seat, but suggests it built the entire car and is now merely pretending to be a passenger. In 2015, cognitive scientist Donald Hoffman presented a theory so audacious it reframes everything we think we know about existence. He proposes that space, time, and material objects are not fundamental features of the universe. They are not the building blocks of reality. Instead, they are nothing more than a user interface, a simplified desktop of icons that our consciousness has constructed to help us navigate a reality far too complex and alien for us to comprehend directly. Hoffman arrived at this astonishing conclusion not from quantum physics, but from a rigorous application of evolutionary game theory to the problem of perception. He asked a simple but profound question: did evolution shape our senses to see the truth? His mathematical models delivered a resounding and counterintuitive answer: no. Evolution shapes our senses for one thing, and one thing only: fitness. The sole purpose of our perception is to give us information that enhances our chances of survival and reproduction. Seeing the unvarnished truth is often a terrible strategy for this. Imagine a prehistoric human trying to understand the true, quantum weirdness-filled nature of a tiger. The complex wave functions and probability fields are meaningless. What they need is a simple, useful icon, a streamlined symbol of tiger that comes pre-loaded with the properties dangerous and run. Hoffman argues that our entire perceptual reality is exactly this: a highly simplified, species-specific dashboard of symbols. The apple on your desk isn't a fundamentally solid, red, round object. Your consciousness is simply generating that specific set of icons: redness, roundness, solidity, because that combination has been evolutionarily useful for a creature like you to interact with whatever that underlying reality actually is. The true nature of the apple and of everything else remains completely hidden behind the veil of perception. So if the physical world is just an interface, what is the real reality that lies beneath the desktop? Hoffman's answer is as elegant as it is extraordinary. He proposes that the fundamental stuff of the universe is not matter or energy, but consciousness itself. More precisely, he defines the cosmos as a vast, dynamic network of what he calls conscious agents. These are not necessarily conscious beings like us. They are the most basic, irreducible units of experience. Think of them as the atoms of consciousness. A single conscious agent might have just the most minimal experience possible, perhaps a single bit of awareness, a faint yes or no experience. Hoffman's mathematical framework then shows how these simple agents can interact and combine, forming more complex networks that give rise to the rich tapestry of experiences we have, and crucially, to the shared perceptual interface that we all mistake for an objective external world. In this view, your mind and my mind are not isolated products of our brains. They are nodes in this vast network, and the physical world of spacetime is the common user interface that our collective consciousness projects to facilitate interaction. The brain, then, is not the source of consciousness, but rather a kind of receiver or filter, a tool that the conscious agent uses to interact with this shared perceptual realm. When Hoffman first presented his theory, the reaction from the scientific community was unsurprisingly a mixture of fascination and deep skepticism. To many physicists and biologists, it sounded less like science and more like a modern version of philosophical idealism, the age-old idea that reality is fundamentally mental. The theory was criticized for being untestable, for pushing the hard problem of consciousness, how subjective experience arises from matter, into an even more mysterious realm. If everything is consciousness, what are the laws that govern these interactions? How could we ever design an experiment to detect a conscious agent? The theory seemed to dissolve into metaphysics, yet Hoffman, a respected scientist with a background in computational psychology, insists his model is mathematically precise and will eventually yield testable predictions. He is actively working on ways to connect his framework to specific quantum mechanical phenomena, suggesting that the collapse of the wave function might be related to the choices made by these interacting conscious agents. The profound implication of Hoffman's proposal is that it completely inverts our standard materialist worldview. For centuries, science has operated on the assumption that matter is primary, and that consciousness is a late-coming, accidental byproduct, an ephemeral ghost in the biological machine. Hoffman turns this on its head. He argues that consciousness is the fundamental reality, and the physical world is the derivative phenomenon. Matter is not the cause of mind. Mind is the cause of matter. This doesn't mean the world is an illusion in the sense of being unreal. The icons on your computer desktop are real. They are just not the reality of the circuits and electricity doing the work. They are a representation, a useful fiction. In the same way, the world we see is a real representation, but it is a catastrophic mistake to confuse the map for the territory. This idea forces us to consider that the deepest truths about the cosmos might not be found by building bigger telescopes or particle colliders to peer deeper into space and time, but by turning inward to understand the nature of the consciousness that is doing the looking. The universe may not be a great physical mechanism, but a great mental reality, and we are not just inhabitants of it, we are participants in its very creation. As we stand back and look at the mosaic formed by these 30 forgotten breakthroughs, a breathtaking picture comes into focus. Though each discovery emerged from a different corner of physics, from the event horizons of black holes to the strange logic of quantum measurement, they are not isolated islands of thought. Instead, they are connected by invisible bridges, all pointing toward a set of revolutionary themes that could redefine the very nature of existence. The most persistent thread running through them all is the idea that information is not just something we discover about the universe. It might be the primary substance from which the universe is made. From Jacob Bekenstein's calculation that a black hole's information content is proportional to its surface area, to the holographic principle suggesting our entire three-dimensional reality is a projection from a two-dimensional surface, we see a consistent demotion of matter and energy in favor of bits and bytes. The universe begins to look less like a collection of physical objects and more like a cosmic computation, an ongoing calculation whose output is the world we experience. This leads us directly to the second profound theme, relationalism, the idea that nothing has properties in and of itself, but only in relation to other things, is echoed again and again. In quantum reference frames, properties are defined relative to an observer. In the transactional interpretation, a quantum event is a handshake between the past and the future. In the AR equals EPR conjecture, the very geometry of space is woven from the relational threads of quantum entanglement. This tells us that the universe is not a static stage with independent actors. It is a dynamic, dancing network of processes and connections. What we perceive as isolated particles and empty space are actually dense knots of relationship in a vast web of interactions. The distance between two stars is not a fundamental void. It is a measure of the lack of quantum connection between them. This is a complete inversion of our classical, intuitive view of reality. And this brings us to the most mind-bending theme of all, the emergence of space and time. For our entire history, we have treated the arena of spacetime as the fundamental given, the unchanging stage upon which the drama of physics plays out. But these breakthroughs suggest that this stage itself is part of the performance. The Wheeler-DeWitt Equation paints a picture of a timeless universe where the flow of time is an illusion. The Amplitudehedron calculates particle interactions without referencing locality or unitarity, the very pillars of spacetime itself. The concept of pregeometry argues that space and time must emerge from something deeper, something more primitive and abstract. Together, they force us to consider that our most basic experiences, the feeling of a moment passing, the certainty that you are here and not there, might be a user interface generated by our consciousness, a simplified dashboard that allows us to navigate a reality far more complex and alien than we can directly perceive. So why were so many of these world-shattering ideas forgotten, sidelined, or met with outright hostility? Their stories reveal a common pattern. They were often victims of their own brilliance, arriving either before the technology existed to test them, like the EPR paradox, or before the mathematical tools were available to formalize them, like David Bohm's Implicate order. They challenged deeply ingrained paradigms, threatening the comfortable, objective reality of Einstein or the pragmatic, shut up, and calculate approach of the post-war physics boom. They dared to blend disciplines like Roger Penrose's foray into consciousness, which made specialists in both physics and neuroscience deeply uncomfortable. And perhaps most importantly, they forced physicists to confront metaphysical questions that seemed outside the realm of empirical science, questions about the nature of time, the role of the observer, and the fundamental architecture of reality. They were not wrong, they were simply premature, their truths too vast and too strange for their time. Yet, in their collective resurrection, we find a powerful lesson about the nature of scientific progress. It is not always a linear march toward truth. It is a messy, human endeavor filled with dead ends, overlooked gems, and ideas that languish in obscurity until the rest of the world catches up. The true path to understanding often lies not in dogmatically following a single paradigm, but in the courageous integration of seemingly disparate ideas. The synthesis of quantum mechanics and general relativity might not come from forcing one to submit to the other, but from finding a third perspective, a deeper language of information, relation, and consciousness that gracefully contains them both. These 30 forgotten breakthroughs are not failures, they are a treasure map, and each one is a crucial piece of the puzzle, guiding us toward a reality that is more interconnected, more mysterious, and more magnificent than we ever dared to imagine. Our journey through these 30 forgotten breakthroughs is more than just a tour of scientific curiosities. It is a powerful reminder that our understanding of reality is always a work in progress, a living conversation across generations of curious minds. Each of these ideas, from the spooky connections of quantum entanglement to the holographic nature of the cosmos, began as a whisper on the fringe, a challenge to the established way of seeing the world. They were often met with resistance, not because they were necessarily wrong, but because they demanded a radical expansion of what we thought was possible. The history of science is filled with such moments where a single voice dares to question the chorus, and in doing so, changes the melody for everyone who follows. This is not a weakness in the scientific process, but its greatest strength, its capacity for self-correction, for humility, and for growth. Max Planck's observation about scientific change can feel cynical, but it also contains a profound truth about human nature. We become attached to our frameworks, to the stories we tell ourselves about how the universe works. Letting go of those stories can be deeply uncomfortable, even for the most brilliant among us. Yet, as we have seen, the universe is under no obligation to conform to our comfort zones. It will continue to be strange, counterintuitive, and magnificent with or without our approval. The true spirit of discovery lies in embracing that strangeness, in allowing ourselves to be humbled and astonished by the sheer creativity of nature. These forgotten breakthroughs are not failures, they are invitations. They invite us to cultivate a mindset of openness, to question our own assumptions with the same rigor we apply to the ideas of others, and to always remain students of the cosmos. This is why your curiosity matters. The questions we ask today, no matter how far out they may seem, could be the seeds of the next great revolution in understanding. The most exciting chapters of physics are likely not behind us in a textbook, but ahead of us, waiting to be written by those who are willing to look at the data and dare to imagine a different story. Perhaps the solution to quantum gravity is hiding in a discarded notebook. Perhaps the key to consciousness is waiting in a misunderstood experiment from 50 years ago. The frontier of knowledge is not a distant line on a map. It is all around us, in the anomalies we ignore and the whispers we dismiss. So let this exploration be a starting point for your own. Dive deeper into the ideas that resonated with you. Read about the visionaries who refused to give up on their heretical thoughts, and never stop wondering about the magnificent, mysterious universe we call home. If this journey through the edges of reality has sparked a sense of wonder in you, please share that feeling. Pass this video along to someone else who loves to question everything. Subscribe to this channel and hit the notification bell, because we have so many more enigmas to explore together, from the nature of time to the mysteries of dark matter. But most importantly, I want to hear from you. Down in the comments, tell me which of these breakthroughs caught your imagination the most. Was it the holographic universe, the possibility that we're living in a simulation, or the haunting idea that spacetime itself is woven from quantum connection? Your thoughts and conversations are what turn a monologue into a dialogue, and together we can keep pushing the boundaries of what we know. Thank you for joining on this incredible journey. Stay curious.